Entropy is one of the most misunderstood yet fundamental concepts in physics, governing everything from the behavior of the universe to everyday phenomena. Ask someone to explain it, and you're likely to hear vague descriptions like disorder or chaos. But entropy is far more profound. It's about energy, information, and the irreversible flow of time itself. Let's start with a thought experiment. Consider a pristine sandcastle standing on a beach. Its grains are meticulously arranged into towers and arches. When the tide washes it away, the grains scatter randomly across the shore, blending into the countless other grains. The sandcastle is gone, replaced by randomness. This journey, from order to a state of higher randomness, captures the essence of entropy. However, entropy isn't simply about chaos. It's about the number of possible configurations a system can take. A sandcastle has a unique arrangement, but the scattered grains have innumerable arrangements. The more possible configurations, the higher the entropy. In the 19th century, physicist Ludwig Boltzmann formalized entropy, showing that it measures the number of microscopic configurations corresponding to a system's macroscopic state. For example, a box of gas can have countless molecular arrangements while maintaining the same temperature and pressure. Similarly, a shuffled deck of cards has far more possible configurations than a perfectly ordered deck, making the shuffled state higher in entropy. This leads us to the second law of thermodynamics, a cornerstone of science. It states that in an isolated system, entropy will either remain constant or increase over time. This principle explains why hot coffee cools instead of heating up. Heat energy spreads into the surrounding air, increasing the entropy of the system. The second law dictates that processes naturally evolve toward higher entropy because these states are more probable. Entropy isn't merely about disorder, it drives processes that shape the world. For instance, nuclear fusion in the sun converts hydrogen into helium, releasing energy that radiates through space. This energy dispersal increases entropy and sustains life on Earth by providing sunlight for photosynthesis. Without this continuous increase in entropy, life as we know it wouldn't exist. One common misconception is equating entropy solely with chaos. While higher entropy often looks messier, it's fundamentally about energy distribution and probability. For instance, a shattered glass on the floor has higher entropy than an intact one because there are far more ways for its pieces to scatter than remain whole. Entropy also defines the arrow of time. Watching a glass shatter makes it clear whether the film is running forward or backward because entropy increases in only one direction. The laws of physics are time-symmetric, meaning they don't inherently distinguish between past and future, but entropy provides the irreversible flow of time we experience. Entropy influences daily routines. For example, making a bed or washing dishes reduces local entropy by creating order, but these actions expend energy and increase entropy elsewhere. Cooking breakfast or cleaning consumes energy that dissipates as heat, contributing to the total entropy of the system. Entropy also limits technological efficiency. In engines, for instance, not all heat generated can be converted into useful work because some energy inevitably disperses, increasing entropy. This fundamental limit is why no machine can ever achieve 100% efficiency. Living organisms may seem to defy entropy because they create complex, ordered systems. However, they do so by exchanging energy and matter with their surroundings. Humans consume food to build and sustain order within their bodies, but release heat and waste into the environment, thereby increasing entropy. Life doesn't violate the second law, it operates within it. Even creativity reflects entropy. When solving problems, our minds explore numerous configurations of ideas before arriving at a solution, much like how systems naturally explore higher probability states. Entropy's connection to information theory is profound. Claude Shannon demonstrated that randomness and information are mathematically linked. For instance, a book in an unfamiliar language may appear as random symbols, high entropy, but to a fluent reader, it is packed with meaning. Data compression works by reducing redundancy and lowering entropy, highlighting this connection. Rolf Landauer's discovery in the 1960s revealed that erasing information increases entropy, demonstrating a direct link between computation and the second law. Deleting a file releases a tiny amount of heat, illustrating how even digital actions obey thermodynamic laws. The universe began in a state of remarkably low entropy with the Big Bang. Over billions of years, entropy has steadily increased, shaping stars, galaxies, and life. This low entropy beginning explains the arrow of time and the universe's irreversible evolution. Why the universe started this way remains one of physics' great mysteries, with theories ranging from statistical flukes to multiverse hypotheses. Black holes exemplify entropy on a cosmic scale. Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy proportional to the area of their event horizon. This entropy is immense, far exceeding that of the stars that formed them. Black holes emit Hawking radiation, slowly losing mass and increasing the surrounding universe's entropy, eventually evaporating completely. The concept of black hole entropy has led to groundbreaking insights into space-time, quantum mechanics, and the holographic principle, the idea that the universe's information content may be encoded on a two-dimensional surface. If the second law holds true, the universe will ultimately reach maximum entropy, a state known as heat death. In this scenario, all energy is evenly distributed, and no meaningful work can occur. Stars will burn out, galaxies will drift apart, and even black holes will evaporate, leaving a cold, dark cosmos. While sobering, this thought underscores the rarity and beauty of our current moment, a universe teeming with complexity and life. Entropy is more than a concept in physics. It's a lens for understanding the universe, life, and time itself. By exploring its connections to information, computation, and cosmology, we see a world shaped by probability and energy distribution. Entropy reminds us of the impermanence of all things, but also celebrates the fleeting complexity and creativity that emerge along the way. While disorder may be inevitable, it's within this framework that life and meaning thrive. Arrow of time. Time is the thread that weaves our universe together, yet its forward flow, the arrow of time, remains one of the most enigmatic aspects of reality. Beyond entropy and thermodynamics, the arrow of time invites us to ask profound questions. Is time an illusion? Could it ever reverse? And why does it shape not just the physical world, but our memories, decisions, and even the way we construct meaning? The arrow of time is not just about physics, it governs how we experience existence. Our perception of time is deeply tied to our ability to form memories. When we remember, our brains store and retrieve patterns of neural activity representing past events. This process increases entropy in the brain and the environment, aligning with the second law of thermodynamics. But there's more. We don't remember the future because memory works on patterns of cause and effect, which unfold along the arrow of time. Interestingly, researchers in neuroscience suggest that the brain itself might exploit entropy. When we make decisions or plan for the future, we simulate possible outcomes, exploring higher entropy states to account for uncertainty. This ability to model the future while being grounded in the irreversible past is what gives humans a sense of directionality in time. In the quantum realm, the arrow of time becomes murky. The fundamental equations of quantum mechanics are time-symmetric, meaning they work equally well forward or backward. But recent research into quantum entanglement and decoherence provides a potential answer. When particles interact, their quantum states become entangled, and their combined wave functions evolve together. In a system with many particles, interactions with the environment cause quantum coherence to degrade over time, a process called decoherence. This transition from a quantum state to a classical state creates an emergent arrow of time. While individual particles don't experience time directionally, the systems they form, our macroscopic reality, exhibit the forward flow of time as a result of collective behavior. In this view, the arrow of time may not be fundamental, but a product of complex systems, emerging from the quantum chaos of the microscopic world. If time is a river, then black holes are its whirlpools, regions where the fabric of space-time twists and contorts. Near a black hole's event horizon, time slows dramatically due to extreme gravitational effects. From an outside perspective, objects falling toward a black hole appear frozen in time, their descent infinitely slowed. Yet black holes don't just stretch time, they also consume information and increase entropy. The interplay between these processes is a cornerstone of modern physics. Hawking radiation, for instance, allows black holes to emit energy and gradually evaporate. But this raises a paradox. What happens to the information that fell into the black hole? The black hole information paradox suggests a profound link between time, entropy, and the fundamental structure of the universe. One speculative idea is that black holes could act as cosmic time capsules, encoding the arrow of time within their event horizons. As they evaporate, they may release this information back into the universe, potentially resetting entropy in ways we don't yet understand. Could time's arrow ever reverse? Some cosmological theories suggest that in a cyclic universe where expansion is followed by contraction, time might flow backward in a contracting phase. In such a scenario, entropy would decrease and the arrow of time would flip. This raises strange possibilities. Would memories unform, stars reignite, and shattered glasses reassemble? In speculative multiverse models, time could flow differently in other universes. Perhaps in some, entropy increases and then decreases cyclically, creating pockets of reversed time. While these ideas are far from proven, they challenge us to rethink time not as a universal constant, but as a property that depends on context and conditions. Beyond its role in physics, time plays a fundamental role in how we organize and understand the world around us. We use calendars, clocks, and measurements to structure our lives. Concepts like progress, growth, and legacy, all central to human civilization, are inherently tied to the directionality of time. Without time's forward flow, we wouldn't have a sense of history or a way to plan for the future. From a scientific standpoint, the direction of time is crucial for our understanding of cause and effect. If time could reverse, the natural order of events would break down, making it impossible to predict outcomes. The arrow of time ensures that each event follows from the last in a sequence that is irreversible, meaning the patterns of the past can never exactly repeat in the future. While the ultimate direction of time may lead toward the universe's heat death, where energy becomes evenly distributed and processes cease, it is this very progression that allows for complexity, life, and the formation of structures in the universe. The forward march of time drives the processes that power stars, sustain biological evolution, and allow civilizations to rise and fall. It's because time moves forward that the universe has the conditions for dynamic change and development. From the smallest quantum particles to the largest cosmological events, the arrow of time is the thread that connects them all. Time is not simply a dimension in which events unfold. It is the framework through which the universe's history is written, with entropy as the mechanism that guides its flow. Information theory. Information theory is the invisible force that shapes the modern world, yet its principles are often misunderstood or overlooked. At its core, it is the study of how information is measured, transmitted, and understood in a universe governed by entropy and complexity. While it may seem abstract, information theory underpins everything from the internet and telecommunications to biology and quantum physics. To grasp its significance is to gain insight into the fundamental fabric of reality. Imagine you're playing a game of 20 questions. The objective is simple. Someone thinks of an object, and you try to figure out what it is by asking yes or no questions. Each question you ask eliminates possibilities, narrowing down the range of potential answers. The fewer questions you need, the more efficiently you're gathering information. This game, in essence, illustrates the principles of information theory, the quantification of uncertainty, and the transmission of meaningful data. In the mid-20th century, Claude Shannon, often referred to as the father of information theory, formalized these ideas. Working at Bell Labs, Shannon was tasked with improving communication systems, such as telephone lines. He realized that the fundamental challenge was not just noise on the line, but the inherent uncertainty in transmitting a message. Shannon's groundbreaking 1948 paper, A Mathematical Theory of Communication, introduced the concept of information entropy, a measure of the unpredictability or randomness of a message. The higher the entropy, the more uncertain or complex the information. To illustrate, consider flipping a coin. A fair coin has two possible outcomes, heads or tails, with equal probability. Each flip carries one bit of information, a term Shannon coined. A bit is the smallest unit of information, representing a choice between two equally likely outcomes. Now, imagine a biased coin that lands on heads 90% of the time. Because the outcome is more predictable, each flip carries less information. This principle explains why a text filled with random letters has more entropy and requires more bits to encode than a coherent sentence in English. Information theory goes beyond simple coin flips. It addresses the efficiency of encoding messages and the limits of transmitting them through noisy channels. A key insight from Shannon's work is that every communication system has a maximum rate of reliable transmission, known as the channel capacity. For instance, if you're trying to send a message over a crackly phone line, the channel's capacity determines how much of the message can get through without error. Shannon demonstrated that it's possible to approach this capacity by encoding the message in a way that compensates for noise, a principle that laid the groundwork for error-correcting codes used in everything from CDs to satellite communications. The beauty of information theory lies in its universality. It applies not only to human-made systems, but also to natural processes. In biology, for example, DNA can be thought of as a communication channel where genetic information is encoded, transmitted, and decoded. The double helix carries instructions for building proteins, and its structure is remarkably efficient at storing and replicating information. Mutations, akin to noise in a communication channel, introduce variations that drive evolution. Information theory helps biologists quantify the complexity and fidelity of these genetic messages, offering insights into everything from heredity to disease. In neuroscience, information theory sheds light on how the brain processes sensory input. Your eyes, ears, and skin constantly receive signals from the environment, light, sound, touch, and your brain must filter, encode, and interpret this barrage of information. The retina, for example, acts as a data compressor, reducing the vast amount of visual input into a manageable stream of signals sent to the brain. This process mirrors the compression algorithms used in digital images and videos, where redundant or less significant data is discarded to save space. Perhaps one of the most intriguing applications of information theory is in understanding the nature of reality itself. Theoretical physicists have begun to explore the idea that the universe operates like a giant informational system, where physical laws are akin to codes, and space-time is a medium for transmitting data. This perspective is especially prominent in quantum mechanics, where the concept of quantum information challenges traditional notions of locality and causality. Quantum entanglement, for instance, can be seen as a form of information transfer that defies classical constraints, linking particles across vast distances instantaneously. Yet information theory also highlights the limits of knowledge. The uncertainty principle in quantum mechanics, which states that certain pairs of properties, like position and momentum, cannot be precisely measured simultaneously, can be reinterpreted through the lens of information. It reveals that there is a fundamental trade-off between the information we can gather about one property and another. Similarly, in classical systems, chaos theory shows how small uncertainties in initial conditions can grow exponentially, making long-term predictions impossible despite deterministic laws. Another fascinating implication of information theory is its relationship with entropy in thermodynamics. At first glance, thermodynamic entropy and information entropy might seem unrelated. The former describes the disorder of physical systems, while the latter quantifies uncertainty in messages. However, they are deeply interconnected. In the 19th century, physicist Ludwig Boltzmann showed that entropy is linked to the number of microscopic configurations that correspond to a macroscopic state. Shannon's work extended this idea to the realm of information, showing that entropy is a measure of missing information about a system's state. This connection has profound implications for understanding the flow of time, as the increase in entropy aligns with the arrow of time we experience. In the digital age, information theory underpins technologies that have transformed society. The Internet, for example, relies on protocols that encode, transmit, and decode vast amounts of data efficiently. Video streaming platforms, online communication, and even artificial intelligence owe their existence to principles first articulated by Shannon. Compression algorithms, such as those used in JPEG images or MP3 audio files, reduce file sizes without sacrificing quality by eliminating redundant data. These algorithms embody the trade-offs and efficiencies at the heart of information theory. Despite its ubiquity, information theory is still evolving. Researchers are exploring its applications in emerging fields like quantum computing, where information is encoded in quantum bits, or qubits, that can exist in superpositions of states. Unlike classical bits, which are either 0 or 1, qubits can represent multiple possibilities simultaneously, enabling unprecedented computational power. However, quantum systems are also highly susceptible to noise, and understanding how to correct errors in these systems requires a deep understanding of both classical and quantum information theory. As we continue to uncover the secrets of information, one thing becomes clear. Information is not just a tool for understanding communication systems or building technology. It is a fundamental aspect of the universe, a thread that weaves together physics, biology, and human experience. From the codes in our DNA to the algorithms that guide spacecraft to distant planets, information shapes our reality in ways both profound and subtle. Information theory teaches us that at the heart of complexity lies a simple, elegant truth. The universe is a conversation, and we are part of the dialogue. Quantum uncertainty. Quantum uncertainty is one of the most profound and misunderstood concepts in physics, a principle that challenges our classical notions of reality and forces us to rethink the very fabric of existence. At its heart lies the idea that, at the quantum level, nature is inherently probabilistic. This isn't just a matter of technological limitation or insufficient measurement tools. It's a fundamental feature of the universe. To understand quantum uncertainty, imagine trying to measure the position and speed of a car on a highway. In classical physics, this task is straightforward. You note where the car is and how fast it's going, and with these two pieces of data, you can predict where it will be in the future. But in the quantum world, the rules change. If the car were a quantum particle, the more precisely you tried to measure its position, the less certain you would be about its speed, and vice versa. This phenomenon is encapsulated in Werner Heisenberg's uncertainty principle, one of the cornerstones of quantum mechanics. The uncertainty principle is often misunderstood as a limitation of our measurement tools, but it's much deeper than that. It's not that we're bad at measuring, it's that the very act of measurement alters the system being observed. In classical physics, you can shine a flashlight on a moving object without affecting its motion. In the quantum realm, observing a particle requires interaction. usually with photons or other particles, and this interaction inevitably disturbs the particle's state. Imagine trying to locate a tiny marble in a dark room by bouncing tennis balls off it. Each collision would move the marble, making it impossible to pinpoint its exact location and motion simultaneously. This analogy, though imperfect, illustrates the fundamental trade-off between knowing a particle's position and its momentum. The more accurately you determine one, the fuzzier the other becomes. At first glance, this uncertainty might seem like a minor quirk of physics, relevant only to scientists working with subatomic particles. But its implications are far-reaching and challenge the deterministic worldview of classical physics. In Newtonian mechanics, if you know the position and velocity of every particle in the universe, you can, in theory, predict the future with perfect accuracy. This idea, known as Laplace's determinism, is incompatible with quantum uncertainty. At the quantum level, the universe is not a clockwork machine, but a probabilistic system governed by probabilities and wave functions. A wave function is a mathematical description of a quantum system that encodes the probabilities of various outcomes. When a particle is not being observed, its wave function describes a range of possible states. For example, an electron around an atom doesn't have a single, well-defined position, but exists as a cloud of probabilities, a smeared-out region where it is likely to be found. This is not just a matter of ignorance or incomplete information. It's a fundamental aspect of quantum reality. The probabilistic nature of quantum mechanics becomes even stranger when we consider the process of measurement. Before measurement, a particle exists in a superposition of states where multiple possibilities coexist. When you measure the particle, the wave function collapses to a single outcome. For instance, if you measure the position of an electron, the wave function collapses to a specific location, and all other possibilities vanish. But what causes the collapse, and why does measurement have this effect? These questions remain among the deepest mysteries of quantum mechanics. Quantum uncertainty also has profound implications for our understanding of energy and time. Just as there's a trade-off between position and momentum, there's a similar uncertainty relationship between energy and time. This principle allows for brief violations of the conservation of energy, leading to phenomena like virtual particles. These are particles that appear and disappear in an instant, playing a crucial role in processes such as the interactions between particles in a vacuum. Although they exist only fleetingly, their effects can be measured and have real consequences, such as the Casimir effect, where two uncharged plates in a vacuum are drawn together by the energy of virtual particles. The implications of quantum uncertainty extend far beyond the laboratory. For example, it plays a crucial role in the stability of atoms. Electrons in an atom cannot spiral into the nucleus, as classical physics might predict, because the uncertainty in their momentum would become infinitely large. This quantum fuzziness creates a balance that prevents the collapse of matter as we know it. Moreover, quantum uncertainty challenges our understanding of causality and locality. In classical physics, causes precede effects, and interactions occur locally. But in the quantum realm, particles can become entangled, forming a mysterious connection where the state of one particle is instantly correlated with the state of another, regardless of the distance between them. This phenomenon, known as quantum entanglement, doesn't violate the uncertainty principle, but complements it, showing that the quantum world operates under a set of rules fundamentally different from those of classical physics. Quantum uncertainty also plays a pivotal role in technological advancements. Quantum cryptography, for example, relies on the principles of quantum mechanics to create secure communication channels. The inherent uncertainty of quantum systems ensures that any attempt to eavesdrop on a quantum communication channel will disturb the system and be detected. Similarly, quantum computing leverages the probabilistic nature of quantum mechanics to perform calculations far beyond the reach of classical computers. By encoding information in qubits, which can exist in superpositions of states, quantum computers can solve complex problems more efficiently than traditional systems. Yet, despite its successes, quantum uncertainty forces us to confront profound philosophical questions. If reality at its most fundamental level is probabilistic, what does this mean for free will and determinism? Are the outcomes we observe truly random, or is there a deeper hidden layer of reality yet to be discovered? These questions echo through the history of physics, from Einstein's famous objection that God does not play dice with the universe to contemporary debates about the interpretation of quantum mechanics. The Copenhagen interpretation, one of the most widely accepted frameworks, embraces the probabilistic nature of quantum mechanics and views the wave function as a complete description of reality. In contrast, interpretations like the many worlds hypothesis suggest that all possible outcomes of a quantum measurement occur in parallel universes, with the observer experiencing only one. Others, like Bohmian mechanics, introduce hidden variables to restore determinism, though these theories often require abandoning the principle of locality. Quantum uncertainty also resonates with our understanding of complexity and chaos in macroscopic systems. While classical chaos theory deals with deterministic systems that are highly sensitive to initial conditions, quantum mechanics introduces a layer of fundamental unpredictability. This interplay between chaos and uncertainty shapes phenomena ranging from weather patterns to the behavior of complex molecules, showing that quantum principles can influence the macroscopic world in subtle yet profound ways. In the end, quantum uncertainty is not just a mathematical abstraction or a feature of microscopic particles. It is a window into the nature of reality itself. It reveals a universe that is not rigid and deterministic, but fluid and probabilistic, where possibilities outweigh certainties and observation shapes existence. This understanding not only advances science, but also invites us to embrace the mystery and wonder of a cosmos governed by laws that challenge our intuition and expand our horizons. Wave-particle duality. Wave-particle duality is one of the most fascinating and counterintuitive principles in physics, challenging our conventional understanding of the universe. Imagine light streaming through your window on a sunny day. To the naked eye, it seems continuous and smooth, illuminating your room with warmth. But delve into its nature, and you discover an astonishing truth. Light behaves both as a wave and as a particle, depending on how you observe it. This duality, simple yet profound, forms a cornerstone of quantum mechanics and has redefined how we perceive reality. To grasp wave-particle duality, it's helpful to start with the historical journey that led to its discovery. For centuries, scientists debated whether light was a wave or a particle. In the 17th century, Isaac Newton championed the idea of light as a particle, or corpuscle, explaining phenomena like reflection and refraction. Around the same time, Dutch physicist Christian Huygens proposed that light behaved as a wave, emphasizing its ability to bend around obstacles and interfere with itself. These two views seemed irreconcilable, each supported by experimental evidence but failing to explain the full range of light's behavior. The wave theory gained significant support in the early 19th century when Thomas Young conducted his famous double-slit experiment. Young shone light through two narrow slits onto a screen and observed an interference pattern, a series of bright and dark fringes, indicating that light waves were overlapping and interfering. This result was difficult to explain if light were merely a stream of particles. The wave theory seemed vindicated, and for a time, the debate was settled. Then came the dawn of the 20th century, which shattered this apparent consensus. In 1905, Albert Einstein published a groundbreaking paper on the photoelectric effect, where he explained that light could eject electrons from a metal surface. Crucially, the energy of these ejected electrons depended not on the brightness of the light, but on its frequency. To explain this, Einstein proposed that light was composed of discrete packets of energy called photons. Each photon carried energy proportional to its frequency, a relationship expressed as E/hf, where h is Planck's constant and f is the frequency of light. This particle-like behavior of light revived the idea that light was not just a wave, but also a particle. Einstein's work earned him the Nobel Prize in 1921 and forced scientists to grapple with an uncomfortable truth. Light could exhibit both wave-like and particle-like properties depending on the context. But the story didn't end with light. As quantum mechanics developed, researchers discovered that electrons, traditionally thought of as particles, could also display wave-like behavior. This revelation extended wave-particle duality beyond light to encompass all matter, a concept formalized in Louis de Broglie's hypothesis. De Broglie proposed that particles like electrons have an associated wavelength inversely proportional to their momentum. This idea was experimentally confirmed in 1927 when Clinton Davison and Lester Germer demonstrated electron diffraction by passing electrons through a crystal lattice. The resulting interference pattern mirrored the behavior of light in Young's double-slit experiment, showing that matter, too, could act as a wave. To visualize this duality, consider water ripples spreading across a pond after a stone is thrown. These ripples represent wave-like behavior, characterized by properties such as wavelength and frequency. Now imagine the stone itself. It's a localized object with a definite position and momentum, akin to a particle. Wave-particle duality suggests that quantum entities like photons and electrons are simultaneously like the ripples and the stone, embodying both natures but never both at the same time during observation. This brings us to the critical role of measurement in quantum mechanics. When we observe a particle, its wave-like nature appears to collapse, and it manifests as a particle at a specific location. But when unobserved, it exists as a wave of probabilities, a mathematical description of all possible outcomes. This duality isn't a limitation of our instruments or knowledge. It's a fundamental aspect of reality. Wave-particle duality becomes even more mysterious in the context of the modern double-slit experiment conducted with single particles like electrons. When electrons are fired one at a time through two slits, an interference pattern still emerges over time, suggesting that each electron behaves as a wave and interferes with itself. But if we place detectors at the slits to determine which slit an electron passes through, the interference pattern disappears, and the electrons behave like particles. This phenomenon underscores the role of the observer in shaping reality and raises profound philosophical questions about the nature of existence. The implications of wave-particle duality are far-reaching, influencing fields from quantum computing to cosmology. In quantum computing, the wave-like superposition of qubits, quantum bits, allows them to perform multiple calculations simultaneously, promising unprecedented computational power. In cosmology, wave-particle duality helps explain phenomena like the cosmic microwave background radiation and the behavior of particles in the early universe. But perhaps the most profound impact of wave-particle duality lies in its philosophical implications. It challenges classical notions of determinism and objective reality, suggesting that the universe at its most fundamental level is not a collection of distinct objects, but a web of probabilities and relationships. It forces us to abandon binary thinking, wave or particle, this or that, and embrace a more nuanced understanding of reality. Wave-particle duality also invites us to reflect on the limitations of human perception. Our everyday experiences are governed by classical physics, where objects have definite properties and trajectories. Quantum mechanics operates in a realm where such certainties dissolve, and entities exist in a state of ambiguity until observed. This discrepancy reminds us that our intuition, shaped by macroscopic experiences, may be ill-suited to grasp the true nature of the universe. Despite its successes, wave-particle duality remains an active area of research and debate. Different interpretations of quantum mechanics offer varying perspectives on the meaning of duality. The Copenhagen interpretation accepts the probabilistic nature of quantum mechanics and the necessity of wave-function collapse during measurement. In contrast, the many worlds interpretation posits that all possible outcomes occur in parallel universes, eliminating the need for collapse. Other interpretations, like Bohmian mechanics, introduce hidden variables to restore determinism while preserving wave-particle duality. Wave-particle duality also sparks questions about the relationship between quantum mechanics and relativity. While quantum mechanics describes the behavior of particles at microscopic scales, general relativity governs the large-scale structure of spacetime. Reconciling these two theories into a unified framework remains one of the greatest challenges in physics, and wave-particle duality may hold clues to this elusive goal. In the end, wave-particle duality is not just a scientific concept. It's a profound reminder of the universe's complexity and mystery. It teaches us that reality is not always as it seems, and that understanding the cosmos requires humility, creativity, and an openness to the unknown. By embracing wave-particle duality, we step closer to unraveling the enigmas of existence, one wave and one particle at a time. Quantum superposition. Imagine flipping a coin. In our macroscopic world, the coin will either land heads or tails. But in the quantum realm, particles can exist in a superposition, a state where they are effectively both heads and tails at the same time, at least until someone observes them. It's not just that we don't know the outcome. The coin genuinely exists in multiple states simultaneously. This bizarre phenomenon defies classical logic and challenges our understanding of reality. To understand superposition, we first need to grasp the quantum world's probabilistic nature. In classical mechanics, the behavior of objects is predictable if you know their initial conditions. Throw a ball into the air, and its path can be calculated with precision. In quantum mechanics, however, particles like electrons or photons don't follow definite trajectories. Instead, their behavior is described by a wave function, a mathematical equation that encapsulates all the possible states a particle could be in. When we say a particle is in a superposition, we mean its wave function represents multiple states simultaneously. A famous thought experiment that illustrates this concept is Schrödinger's cat. In this scenario, a cat is placed in a sealed box with a vial of poison, which will be released if a quantum particle inside the box decays. The particle's state, decayed or not decayed, is governed by quantum superposition, meaning it exists in both states until measured. Consequently, the cat is considered both alive and dead until someone opens the box and observes it. While absurd, this thought experiment underscores how quantum superposition leads to paradoxical situations when applied to macroscopic objects. The superposition principle was first introduced in the early 20th century as physicists grappled with the behavior of particles on atomic and subatomic scales. Experiments with light and electrons, such as the double-slit experiment, revealed patterns that could only be explained if particles acted as waves. When particles like electrons are fired one at a time through two slits, they create an interference pattern on a detector screen, a hallmark of wave behavior. This pattern emerges only if the particles exist in a superposition of going through both slits simultaneously. Quantum superposition isn't just a theoretical abstraction, it has been experimentally verified many times. For instance, in 2010, scientists at the University of California created a superposition state in a tiny object visible to the naked eye, a small metal paddle. Although not as large as Schrödinger's hypothetical cat, this experiment demonstrated that superposition isn't confined to the microscopic realm and hinted at the boundary between the quantum and classical worlds. But what happens to a superposition when we observe it? Here lies one of the most mysterious aspects of quantum mechanics. According to the Copenhagen interpretation, the act of measurement causes the wave function to collapse, forcing the particle to choose a specific state. Before measurement, the particle exists in a cloud of probabilities, but observation pins it down to a single outcome. This raises profound questions. What constitutes an observation? Does consciousness play a role, or can any interaction with the environment collapse the wave function? The relationship between superposition and measurement has practical implications in fields like quantum computing. Quantum computers leverage qubits, which can exist in superpositions of 0 and 1, unlike classical bits that are strictly 0 or 1. This property allows quantum computers to perform many calculations simultaneously, vastly increasing their potential power for certain tasks. For example, superposition enables quantum algorithms to factorize large numbers or search databases exponentially faster than classical algorithms. Superposition also plays a role in quantum cryptography, offering unprecedented security for communication. In a protocol like quantum key distribution, the superposition states of particles are used to encode information. Any attempt to eavesdrop collapses the superposition, making tampering detectable and ensuring secure communication. One of the most intriguing applications of superposition is in the study of quantum biology. Some researchers propose that processes like photosynthesis or bird navigation involve quantum superposition. In photosynthesis, for example, superposition might help energy move efficiently through a plant's light harvesting complexes by exploring all possible paths simultaneously. Similarly, certain birds are thought to use quantum effects in their visual systems to detect Earth's magnetic field, aiding in navigation. Yet, quantum superposition raises as many questions as it answers. Why don't we experience superposition in our everyday lives? The answer may lie in a phenomenon called decoherence. When a quantum system interacts with its environment, the superposition states become entangled with the environment's many particles. This interaction effectively smears out the superposition, making it impossible to observe in macroscopic systems. Decoherence explains why quantum behavior is typically confined to microscopic scales, and why Schrödinger's cat, in practice, would not be both alive and dead. The many worlds interpretation of quantum mechanics offers an alternative explanation. According to this view, every possible outcome of a quantum event occurs in a separate, branching universe. In the case of Schrödinger's cat, the cat is alive in one universe and dead in another. While this interpretation avoids the need for wave function collapse, it introduces a mind-boggling implication: an infinite number of parallel realities, each corresponding to a different outcome of every quantum event. Quantum superposition also touches on philosophical questions about the nature of reality. Is the quantum world inherently probabilistic, or does it hide a deterministic framework that we have yet to uncover? The debate between determinism and randomness has implications for free will, causality, and the very fabric of existence. Even in the context of cosmology, superposition offers insights. The early universe is thought to have existed in a superposition of quantum states, with its evolution governed by quantum fluctuations. These fluctuations left imprints in the cosmic microwave background radiation, shaping the large-scale structure of the universe we observe today. Understanding superposition in this context could provide clues about the origins of the universe and the fundamental nature of space-time. Superposition's counterintuitive nature also challenges our intuitions and encourages us to think beyond classical boundaries. It invites us to question the assumptions we take for granted, that objects have definite properties, that time flows uniformly, and that reality is independent of observation. By embracing the paradoxes of superposition, we open ourselves to a deeper understanding of the universe's mysteries. Ultimately, quantum superposition is more than a scientific concept. It's a profound reminder of the universe's complexity and the limits of human perception. It reveals a world where particles can exist in multiple states, where observation shapes reality, and where the boundaries between certainty and possibility blur. This principle not only advances our knowledge of quantum mechanics, but also inspires a sense of wonder and curiosity about the nature of existence itself. Schrödinger's Cat Paradox. Schrödinger's cat is one of the most famous thought experiments in quantum mechanics, often used to highlight the paradoxical and counterintuitive nature of quantum theory. But what does it really mean? How does it challenge our understanding of reality? And why has it sparked so much debate since its introduction? At first glance, the idea of a cat existing in two contradictory states, both alive and dead, seems absurd. Yet at the heart of this paradox lies a deep exploration of the nature of observation, the role of the observer, and the fundamental laws of the quantum world. Erwin Schrödinger, an Austrian physicist, formulated this thought experiment in 1935 to critique the Copenhagen interpretation of quantum mechanics, which was the dominant theory of the time. The Copenhagen interpretation suggests that quantum systems exist in a superposition of states until they are observed or measured, at which point their wave function collapses into a single state. In this context, Schrödinger's cat is a way to explore the strange and often nonsensical implications of this theory when applied to macroscopic everyday objects like a cat. Imagine this scenario: a cat is placed inside a sealed box, along with a radioactive atom, a Geiger counter, a vial of poison, and a hammer. The setup is designed so that if the Geiger counter detects radiation, a random quantum event, it triggers the hammer to break the vial of poison, killing the cat. If no radiation is detected, the cat remains alive. Now, because the radioactive atom is subject to quantum uncertainty, it exists in a superposition of decayed and undecayed states. According to quantum mechanics, until someone opens the box and observes the system, the atom is both decayed and not decayed, and as a result, the cat is both alive and dead, simultaneously. This is where the paradox lies. In the quantum world, particles like electrons or photons can exist in multiple states at once, a phenomenon known as superposition. But when these ideas are applied to a cat, something that clearly exists in one definite state or the other, our intuition breaks down. The idea that the cat can be alive and dead at the same time seems absurd and impossible, but quantum mechanics doesn't seem to care about our classical intuition. The key to Schrödinger's cat paradox lies in the interpretation of quantum mechanics. According to the Copenhagen interpretation, when no one is observing the system, all the possibilities, alive or dead, coexist in a superposition. It's only when the system is measured, that is, when the box is opened and an observer looks inside, that the wave function collapses into one state. This collapse process, how and why a quantum system chooses a particular state, is one of the great mysteries of quantum mechanics. In the Schrödinger's cat experiment, before the box is opened, the cat is in a superposition of both alive and dead. But this presents a serious problem. How can a cat, a macroscopic object, exist in such a strange quantum state? In the world we see around us, objects are either alive or dead, not both. This contradiction suggests a fundamental issue with applying quantum mechanics to larger everyday objects. One possible explanation is that quantum superposition is only relevant to microscopic particles, such as electrons or atoms. Macroscopic objects like cats, on the other hand, are made up of vast numbers of particles, and interactions between these particles with their environment lead to decoherence. Decoherence is a process by which quantum superposition breaks down when a system becomes entangled with its environment, causing the system to behave in a classical manner. In other words, while the atom inside the box may be in a superposition of states, the cat, being part of a larger system, will experience decoherence and appear to be either alive or dead, not both. This brings us to another question. What exactly counts as an observer? The Copenhagen interpretation suggests that the collapse of the wave function occurs when someone measures or observes the system. But this raises deep questions about the role of consciousness in the quantum world. Does the cat state depend on whether a human being opens the box? Or does any interaction with the environment, even without human observation, cause the wave function to collapse? Some interpretations, like the many worlds hypothesis, suggest that all possible outcomes of a quantum event occur, each in a separate parallel universe. In the case of Schrödinger's cat, there would be one universe in which the cat is alive, and another in which it is dead. The observer doesn't collapse the wave function. Instead, they experience only one of the outcomes, with the other branches existing in different realities. Other interpretations of quantum mechanics, such as the objective collapse theories, suggest that the wave function doesn't collapse only when observed, but rather spontaneously collapses when it reaches a certain threshold of complexity. In these interpretations, the cat might still be alive and dead simultaneously until the system reaches a critical point that forces the collapse. Some physicists have proposed that there might be a fundamental underlying cause for the collapse of the wave function, which occurs independently of observation or measurement. The Schrödinger's Cat Paradox challenges the very nature of reality itself. What does it mean for something to exist in two states at once? How do we reconcile the quantum world of probabilities with our everyday experiences of definite, well-defined objects? Is reality fundamentally probabilistic, or is there a deeper deterministic explanation that we simply haven't uncovered yet? The thought experiment also raises important questions about the relationship between quantum mechanics and classical physics. Why do large macroscopic objects like cats behave according to the laws of classical physics, while microscopic particles obey the laws of quantum mechanics? The interface between the quantum and classical worlds is a central area of research in physics, with ongoing attempts to understand how classicality emerges from quantum systems. This quest to understand the classical limit of quantum mechanics has led to some interesting developments, such as the study of quantum to classical transitions and the role of decoherence in everyday phenomena. Schrödinger's cat paradox also has implications for the field of quantum computing. Quantum computers rely on the principles of superposition and entanglement to perform calculations far more efficiently than classical computers. In a quantum computer, qubits can exist in a superposition of both 0 and 1, allowing quantum computers to perform many calculations simultaneously. However, just like Schrödinger's cat, quantum computers rely on the collapse of the wave function when a measurement is made. Understanding how and when this collapse occurs is critical for ensuring the stability and reliability of quantum computing systems. While Schrödinger's cat paradox was originally designed as a critique of quantum mechanics, it has become an essential part of the quantum conversation. It forces us to confront the limitations of our intuition and to reconsider our notions of reality, observation, and measurement. It highlights the profound differences between the world we experience every day and the bizarre world of quantum mechanics, where particles can be in multiple states at once and where the act of observation plays a crucial role in determining outcomes. The Schrödinger's cat thought experiment remains a powerful tool for exploring the foundations of quantum mechanics, shedding light on the mysteries of superposition, wave function collapse, and the role of the observer in the quantum world. It may seem like an absurd scenario, but it forces us to rethink our deepest assumptions about reality itself, making it one of the most profound and enduring ideas in modern physics. Fundamental particle. Fundamental particles are the building blocks of everything we see in the universe, from the smallest grain of sand to the largest galaxies. Yet, for all their importance, they are notoriously elusive and difficult to understand. They don't behave like anything we encounter in our daily lives, and our classical intuition fails us when we try to picture them. To comprehend the true nature of fundamental particles, we must journey into the strange and perplexing realm of quantum mechanics. At its core, the idea of a fundamental particle refers to the smallest unit of matter that cannot be broken down into anything simpler. For centuries, scientists believed that atoms were the ultimate building blocks of matter. But as research in physics advanced, we discovered that atoms themselves are made up of even smaller particles, which are not only the foundation of all matter, but also the key to understanding the very forces that govern the universe. The story begins with the discovery of the atom. In the early 19th century, John Dalton proposed that all matter was made up of indivisible particles, which he called atoms. However, it wasn't long before scientists realized that atoms themselves were far from indivisible. In the early 20th century, experiments by scientists such as J. Thomson, Ernest Rutherford, and Niels Bohr revealed that atoms were made up of a nucleus of protons and neutrons surrounded by a cloud of electrons. This discovery set the stage for the next phase of particle exploration, the study of subatomic particles. As technology advanced, particularly with the advent of particle accelerators, physicists began to uncover even more mysterious particles. Through these experiments, it became clear that protons, neutrons, and electrons were not the final pieces of the puzzle. They were, in fact, composed of even smaller particles. This led to the development of the Standard Model of particle physics, which describes the fundamental particles that make up all matter and the forces that act on them. The Standard Model categorizes the fundamental particles into two main groups, fermions and bosons. Fermions are the particles that make up matter, while bosons are the force carriers that mediate the fundamental forces of nature. Let's dive deeper into these categories to understand what they mean. Fermions are particles that obey the Pauli exclusion principle, which states that no two identical fermions can occupy the same quantum state simultaneously. These particles include quarks and leptons, which combine to form all the matter in the universe. There are 6 types of quarks: up, down, charm, strange, top, and bottom, and 6 types of leptons, including the electron, the muon, and the tau, as well as their corresponding neutrinos. Quarks are never found in isolation. They always combine in groups to form composite particles such as protons and neutrons. Electrons, on the other hand, are stable particles that orbit atomic nuclei and are responsible for chemical reactions. Quarks are held together by the strong nuclear force, which is mediated by particles called gluons. This force is incredibly powerful at short distances, which is why quarks are confined within larger particles like protons and neutrons. Gluons are themselves massless, but they carry a property called color charge, which determines how quarks interact with one another. This concept of color charge is analogous to the way electric charge works, but it operates on a different scale and is unique to the strong force. Leptons, on the other hand, are not affected by the strong force. Instead, they interact through the electromagnetic force and the weak nuclear force. Electrons, for instance, interact with the electromagnetic force, which is responsible for electricity and magnetism, while neutrinos interact through the weak force, which is responsible for certain types of radioactive decay. Although neutrinos are incredibly elusive and difficult to detect, they are among the most abundant particles in the universe. Bosons are the force carriers of nature. While fermions make up matter, bosons mediate the forces that govern the interactions between those particles. The 4 fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are all mediated by different bosons. The photon, for example, is the boson that carries the electromagnetic force. The W and Z bosons mediate the weak nuclear force, which governs processes like radioactive decay. The gluon, as mentioned earlier, is the force carrier for the strong nuclear force. And the Higgs boson, discovered in 2012, is associated with the Higgs field, which gives particles their mass. Among these, the Higgs boson is particularly important because it provides an explanation for why some particles have mass while others do not. According to the Higgs mechanism, particles gain mass by interacting with the Higgs field. The stronger the interaction, the more massive the particle. The discovery of the Higgs boson at CERN was a monumental achievement in particle physics, as it confirmed the existence of the Higgs field and helped to complete the Standard Model. However, the Standard Model, despite its success in explaining the fundamental particles and forces, is not the final word on particle physics. It is incomplete in several key areas. For one, it does not account for gravity, which is described by Einstein's theory of general relativity. The Standard Model also cannot explain the existence of dark matter and dark energy, which make up most of the universe's mass and energy, but remain largely invisible to us. Furthermore, the Standard Model relies on some parameters, such as the masses of the particles, that seem arbitrary and are not explained by the theory itself. This is where the search for new physics beyond the Standard Model comes in. Physicists are constantly looking for ways to extend our understanding of fundamental particles and their interactions. One of the most promising ideas is string theory, which posits that particles are not point-like objects, but rather tiny vibrating strings. These strings can vibrate in different ways, and the different vibrational modes correspond to different particles. If string theory is correct, it could explain why the forces of nature behave the way they do, and provide a unified framework that encompasses all the fundamental forces, including gravity. Another area of active research is the study of neutrinos. These elusive particles have been a mystery for decades, and their discovery has raised many questions about the nature of the universe. Neutrinos have mass, albeit a very small one, and they interact only weakly with other matter. In fact, trillions of neutrinos pass through your body every second without you ever noticing. Understanding neutrinos and their role in the universe could open up new avenues for research in particle physics. The search for dark matter is another major frontier in fundamental particle physics. While we cannot directly observe dark matter, we know it exists because of its gravitational effects on visible matter. Dark matter seems to make up about 27% of the universe's total mass and energy. Some scientists believe that dark matter may be composed of yet undiscovered particles, such as weakly interacting massive particles, WIMPs. Finding these particles could unlock the secrets of dark matter and revolutionize our understanding of the cosmos. As we continue to explore the nature of fundamental particles, we are constantly challenged to rethink our ideas about space, time, and reality itself. The more we learn about these tiny, fundamental components of the universe, the more we realize how much we still don't know. Are there other unknown particles waiting to be discovered? Are there new forces that we haven't yet uncovered? The search for the answers to these questions is one of the most exciting and profound endeavors in modern science. In the end, the study of fundamental particles is not just about understanding the building blocks of matter. It is about understanding the very fabric of the universe. By uncovering the mysteries of the smallest particles, we come closer to grasping the profound truths about the nature of reality, the forces that shape our world, and the origins of the cosmos itself. The journey to uncover these secrets is ongoing, and each discovery brings us one step closer to unlocking the deepest mysteries of existence. Quantum entanglement. Quantum entanglement is one of the most mind-bending concepts in modern physics, so much so that it often feels like it defies all logic and common sense. Imagine a pair of particles, like two electrons, that are created in such a way that their properties become linked together, regardless of the distance between them. Once these particles are entangled, they share information with each other in ways that seem impossible by the rules of classical physics. It's as though no matter how far apart they are, the state of one particle immediately influences the state of the other. To understand this strange phenomenon, let's begin by stepping into the world of quantum mechanics. In the quantum world, particles don't behave like solid, well-defined objects. Instead, they exist in a state of probability, their properties only becoming certain when measured. This is a stark contrast to the world we experience daily, where objects like chairs, cars, and people have predictable, stable properties. But in the quantum realm, things are constantly in flux, existing in multiple states simultaneously until we observe them. This idea is called superposition, and it's a core principle of quantum mechanics. Now, let's take it a step further. Imagine two electrons that are entangled. Before measuring, both electrons are in a superposition of multiple possible states. When you measure one of the electrons, say its spin, a fundamental property of particles, the state of the second electron is immediately determined, no matter how far apart they are. This phenomenon seems to imply that the two particles are somehow connected, sharing information instantaneously, even if one is on Earth and the other is light years away in another galaxy. This is the essence of quantum entanglement. But here's where it gets even more intriguing. Albert Einstein, who famously referred to this idea as spooky action at a distance, found it deeply troubling. According to the theory of relativity, no information can travel faster than the speed of light. Yet, quantum entanglement seems to suggest that information between entangled particles is transmitted instantaneously, violating the limits set by relativity. Einstein wasn't alone in his skepticism. Even Niels Bohr, a major figure in the development of quantum mechanics, was deeply invested in exploring the implications of entanglement. However, decades of experiments have confirmed that entanglement is real, and the results continue to baffle physicists. In the 1960s, physicist John Bell developed a theorem known as Bell's theorem that showed how quantum mechanics predictions about entanglement could be tested experimentally. Bell's theorem suggested that if quantum mechanics were correct, entangled particles would violate certain inequalities that were assumed to hold true in classical physics. Multiple experiments, including those by physicists like Alain Aspect in the 1980s, have consistently supported the predictions of quantum mechanics, demonstrating that entangled particles do indeed violate these classical inequalities. In other words, the weirdness of entanglement isn't just a theoretical concept. It's been confirmed by empirical data. But what does it all mean? Why do entangled particles behave this way, and how can we make sense of it? One possibility is that quantum entanglement is not so much about particles communicating across vast distances, but rather about a deep connection between them that transcends space and time. Instead of viewing particles as independent entities, we can think of them as part of a unified whole, existing within a larger quantum system. This perspective challenges the traditional notions of separateness and individuality that govern classical physics, and pushes us to think about the universe in new, interconnected ways. One analogy often used to help grasp the concept of quantum entanglement is the idea of a pair of gloves. Imagine you have two gloves, one for the left hand and one for the right. You place each glove into separate boxes, then ship the boxes to two different locations far apart from each other. When you open one box and find the left glove, you instantly know that the other box must contain the right glove. The key difference here, of course, is that the gloves are definite objects, whereas quantum entangled particles exist in a state of indeterminacy until they are observed. The act of measuring one particle seems to affect the other particle instantaneously, no matter the distance between them. The connection between the gloves in our analogy is just a classical idea of correlation. Entanglement, however, goes far beyond correlation into the realm of quantum reality. But entanglement does not only challenge our understanding of space and time, it also has profound implications for our understanding of information. In classical physics, information about a system can only be known by measuring it, and that information is constrained by the limits of the speed of light. However, quantum entanglement suggests that information may not be constrained by these limits. This has profound implications for everything from quantum computing to our understanding of the universe itself. One of the most exciting applications of quantum entanglement lies in the field of quantum computing. Quantum computers, unlike classical computers, leverage quantum bits or qubits that can exist in multiple states simultaneously. This superposition of states allows quantum computers to process vast amounts of information at once, making them potentially much more powerful than classical computers. But what makes quantum computing even more remarkable is the role that entanglement plays in enhancing the power of quantum algorithms. When qubits are entangled, they can work together in ways that classical bits cannot, allowing quantum computers to solve problems that would take classical computers millennia to crack. Quantum entanglement also plays a key role in the emerging field of quantum cryptography. In quantum key distribution, for example, the security of communication is based on the principle of quantum entanglement. If two parties share entangled particles, any attempt to eavesdrop on their communication will inevitably disturb the entanglement, alerting them to the presence of a third party. This offers a level of security that classical cryptographic methods cannot provide, making quantum cryptography a promising tool for secure communication in the future. Beyond technology, quantum entanglement raises profound questions about the nature of reality itself. If particles can be instantaneously connected across vast distances, does this imply that the universe is more interconnected than we previously thought? Are there hidden connections between objects and events that we are not yet capable of perceiving? Does entanglement point to a deeper, unified theory of everything, one that could reconcile quantum mechanics with the theory of relativity? As we delve further into the mysteries of quantum entanglement, we find ourselves grappling not only with the strange behavior of particles, but also with the very nature of reality itself. Entanglement forces us to confront the limits of our understanding and challenges us to expand the boundaries of what is possible. It reminds us that the universe, at its most fundamental level, operates according to principles that are far stranger and more wondrous than we can fully comprehend. In the end, quantum entanglement is not just a scientific curiosity. It is a window into the heart of the quantum world, where the familiar rules of classical physics break down, and the strange and mysterious laws of quantum mechanics take center stage. As we continue to explore this strange phenomenon, we move closer to unlocking the deepest mysteries of the universe, and perhaps uncovering the true nature of reality itself. Observer effect. The observer effect is one of the most fascinating and perplexing phenomena in the realm of quantum physics, stirring both excitement and confusion. It's a concept that suggests the act of observing something can actually change its behavior. At first glance, this might seem absurd. After all, how can something as seemingly neutral as simply looking at an object change its properties? The answer, however, lies in the strange, counterintuitive nature of quantum mechanics, where the act of observation doesn't just record the state of a system, it actively participates in shaping it. Let's start by considering an everyday example. Imagine you're trying to measure the temperature of a cup of coffee. You take a thermometer, dip it into the coffee, and read the temperature. In this process, the thermometer merely records the temperature of the coffee without influencing it significantly. You might think this is how all measurements work. When we measure something, we just gather information without altering it. But in the quantum world, things aren't that simple. The very act of measurement can disturb the system being observed in profound ways. At the heart of the observer effect is the concept of superposition. In quantum mechanics, particles don't have definite properties until they are observed. Instead, they exist in a superposition, a blend of all possible states. Take the example of an electron moving in an atom. Rather than following a predictable path as in classical physics, the electron exists in a cloud of possibilities, where it could be in multiple locations at once, with different speeds, spins, and energies. It is only when we measure its position or momentum that this cloud of possibilities collapses into one concrete outcome. In this sense, the observer effect suggests that it's not just our knowledge of a system that changes upon measurement, but the system itself. The most famous illustration of the observer effect comes from the double-slit experiment, a cornerstone of quantum physics. Imagine you have a barrier with two slits, and on the other side, you place a screen that can detect where particles like electrons land. When you shoot electrons at the slits and you're not measuring which slit they go through, the electrons behave like waves. They create an interference pattern on the screen, as if each electron is interfering with itself, passing through both slits simultaneously. However, when you place a detector at the slits to observe which slit the electron goes through, the interference pattern disappears, and the electrons behave like particles again, landing in discrete spots. In this case, the simple act of measuring or observing the electron's path causes it to behave differently. This is where the observer effect takes on a deeper philosophical dimension. If observation changes the behavior of a particle, what does that say about the nature of reality itself? Some physicists and philosophers have suggested that the universe doesn't have definite properties until we observe it. This is a radical departure from our everyday experience, where objects like cars or trees seem to exist independently of whether or not we look at them. In the quantum realm, however, particles seem to be in a state of potentiality, existing in a cloud of probabilities until they are observed. The observer effect thus challenges our understanding of what constitutes reality. Is it that the universe exists only as a collection of possibilities, waiting to be actualized by conscious observation? One of the most famous quotes associated with the observer effect comes from the physicist Niels Bohr, who once said, "Everything we call real is made of things that cannot be regarded as real." In this sense, Bohr was emphasizing the strange, probabilistic nature of reality at the quantum level. Our everyday intuition leads us to believe that things exist with definite properties. An apple is always red. A chair always has 4 legs. But quantum mechanics tells us that at the subatomic level, reality is far more fluid and uncertain. But what does this mean in practical terms? If observation can change the state of a system, what does that mean for the role of the observer in the universe? One theory that has emerged from this is the concept of the participatory universe, proposed by physicist John Archibald Wheeler. Wheeler suggested that the universe itself is in some sense dependent on the observer. In his view, the universe is not a static, pre-existing entity, but rather something that is actively created through the act of observation. This doesn't mean that the universe doesn't exist when we're not looking at it, but it suggests that the universe's properties might be influenced by our perception of it. Wheeler's participatory universe is deeply tied to the notion that consciousness plays a central role in shaping reality. While this is still a controversial idea, it has gained attention in both physics and philosophy, particularly in discussions of quantum mechanics and consciousness. Some theorists suggest that consciousness itself is fundamental to the physical world, and that our observations of quantum systems are not merely passive acts of measurement, but are in some way co-creators of the quantum world we experience. Of course, not all scientists agree with this interpretation. Many believe that the observer effect is simply a result of the limitations of our measurement tools. In this view, the effect doesn't imply that consciousness itself is affecting the particles, but rather that our attempts to measure quantum systems inevitably disturb them. After all, in the double-slit experiment, the mere act of placing a detector at the slits doesn't require human observation. It's the interaction between the measuring device and the particles that causes the change. In this sense, the observer effect may not be about consciousness, but about the unavoidable disturbance caused by any measurement. While these debates continue, the observer effect has profound implications for our understanding of the quantum world and the nature of reality. It shows us that, at the smallest scales, the boundaries between the observer and the observed are much more blurred than we might expect. This is not just a technicality, it's a fundamental shift in how we understand the nature of existence. In a world governed by quantum mechanics, the very act of observing something can alter it, challenging our most basic assumptions about the separation between subject and object, between the perceiver and the perceived. There are also practical applications of the observer effect in modern technology. One of the most exciting fields to emerge from quantum mechanics is quantum computing. Quantum computers exploit the principles of quantum mechanics, including superposition and entanglement, to perform calculations far more efficiently than classical computers. But the observer effect plays a crucial role here as well. In order to extract useful information from a quantum system, it must be measured, but this measurement will inevitably disturb the system, collapsing its superposition into a definite state. This presents a challenge for quantum computing, as it requires the careful management of quantum states and minimizing the disturbance caused by measurement. Quantum cryptography, too, relies on the principles of quantum mechanics, including the observer effect. One of the key features of quantum cryptography is that it's incredibly secure, because any attempt to eavesdrop on the system will disturb the quantum states being transmitted, alerting both parties to the presence of an intruder. In this sense, the observer effect becomes a feature, not a bug, of quantum information systems, providing a level of security that classical encryption methods can't match. The observer effect, therefore, is not just an abstract philosophical question. It has tangible consequences in the real world, affecting everything from the design of quantum computers to the development of secure communication technologies. It challenges our understanding of the universe and forces us to confront the deep interconnectedness between the observer and the observed. Whether we are exploring the nature of consciousness, the structure of reality, or the limits of our technological capabilities, the observer effect serves as a reminder that the universe is far stranger than we might have imagined. In the quantum world, nothing is ever as simple as it seems, and even our simplest acts of observation can change the fabric of reality itself. Quantum tunneling. Quantum tunneling is one of the most mind-bending phenomena in the realm of quantum physics, and it defies our everyday experience in ways that seem almost magical. Imagine a ball rolling toward a hill. In classical physics, if the ball doesn't have enough energy to reach the top of the hill, it simply can't get over it. It will either roll back down or stop at the base. But in the quantum world, things are far stranger. Instead of needing enough energy to climb over the hill, the ball can sometimes just tunnel through the hill itself, appearing on the other side, as if it passed right through the solid barrier. This is the essence of quantum tunneling. Particles that, under normal conditions, should be blocked by barriers can, with a certain probability, pass through them. And this is just the beginning of what makes quantum tunneling so fascinating. At first glance, quantum tunneling seems to be a violation of the most basic principles of classical mechanics, and yet it's a fundamental part of quantum mechanics that has been experimentally verified in countless experiments. How can a particle simply pass through an obstacle it doesn't have enough energy to overcome? To understand this, we need to dive into the peculiar world of quantum mechanics, where particles don't follow definite paths or have precise locations until we measure them. Instead, they exist as probabilities, as waves of potential that can spread out across space, rather than as discrete points. This wave-like nature is what allows quantum tunneling to occur. Imagine, if you will, that a particle, such as an electron, is not confined to a single position in space, but instead exists in a cloud of possibilities. In quantum mechanics, we describe this cloud of possibilities using a mathematical function called a wave function. The wave function gives us the probability of where the particle might be found if we were to measure it. If we apply this idea to the scenario of a particle approaching a barrier, the wave function doesn't simply stop at the barrier. Instead, it starts to gradually decrease as the particle approaches the barrier but can extend beyond it. This means there's a non-zero probability that the particle can be found on the other side of the barrier, even if it doesn't have enough energy to overcome it. It's like a person standing in front of a wall. In classical physics, if they don't have enough speed to jump over it, they simply cannot get to the other side. But in the quantum world, the person's wave function would still extend beyond the wall. There's a tiny probability that, despite not having the energy to jump, they could somehow find themselves on the other side, as if they had magically passed through the wall. This behavior is very much unlike what we see in our everyday world, where classical physics governs the movement of objects. In the quantum realm, particles don't have a definite position until we observe them. Instead, they exist in a superposition of many possibilities, and these possibilities can include things that seem physically impossible in our macroscopic experience, like tunneling through barriers. The probability that a particle will tunnel through a barrier depends on several factors, such as the width and height of the barrier, the particle's energy, and the nature of the wave function. The more the barrier feels like an obstacle to the particle, the less likely it is that the particle will tunnel through it, but it's never impossible. This probability is governed by the Schrödinger equation, the mathematical foundation of quantum mechanics, which describes how the wave function evolves over time. One of the most striking things about quantum tunneling is that it isn't just an abstract concept with no real-world relevance. In fact, quantum tunneling plays a crucial role in many phenomena in both physics and chemistry. For example, quantum tunneling is the reason why nuclear fusion happens in stars. The Sun and other stars generate their energy through nuclear fusion, where hydrogen atoms collide and fuse to form helium, releasing a tremendous amount of energy in the process. However, these hydrogen nuclei, called protons, are positively charged and should repel each other because of the electrostatic force. In classical physics, they would never have enough energy to overcome this repulsion. But in the quantum world, the protons don't need to directly collide with enough energy to overcome the electrostatic repulsion. They can tunnel through the barrier, allowing fusion to occur at the temperatures and pressures present inside stars. Without quantum tunneling, stars wouldn't shine, and life as we know it wouldn't exist. Quantum tunneling also plays a critical role in technologies like scanning tunneling microscopes, which allow scientists to see individual atoms. These microscopes take advantage of the fact that when an electron is tunneled through a barrier, the current can be measured, providing a map of the surface at atomic resolution. Without quantum tunneling, these devices wouldn't function, and our ability to study materials at the nanoscale would be vastly limited. Tunneling also underlies the working principles of devices like tunnel diodes and quantum dot-based technologies, which have numerous applications in electronics and computing. Despite its importance, quantum tunneling remains one of the most difficult concepts to intuitively grasp, and it often raises questions about the nature of reality itself. If particles can tunnel through barriers, does this mean that the universe itself is fundamentally unpredictable, with particles constantly flitting between alternate realities or states? Some interpretations of quantum mechanics suggest that tunneling is a manifestation of the many worlds interpretation, where every possible outcome exists in a separate branch of the universe, and tunneling is just a glimpse into one of those alternate branches. In this view, quantum tunneling isn't a violation of the laws of physics, but a confirmation that all possibilities are played out in parallel worlds. While this interpretation remains speculative, it adds an extra layer of intrigue to the strange phenomenon of tunneling. Another important aspect of quantum tunneling is the concept of the barrier height, how thick and tall a barrier must be for tunneling to occur. In general, the wider and taller the barrier, the less likely tunneling is to happen. But even in the case of very high and thick barriers, there is still a small but non-zero probability that tunneling can occur. This probabilistic nature of quantum tunneling highlights the underlying uncertainty of the quantum world, where we can never be completely sure of what will happen until we observe it. And even then, we can only say what is most likely to happen. Tunneling is also a reminder that the quantum world is governed by probabilities rather than certainties. In classical physics, we are accustomed to thinking that things have definite positions, speeds, and trajectories. But in the quantum realm, particles can be described by probabilities, waves of potential that only collapse into a specific state when observed. This behavior, which seems so alien to our everyday experiences, is at the heart of quantum mechanics, where uncertainty and indeterminacy reign supreme. Quantum tunneling challenges our understanding of how the world works, highlighting the differences between the microscopic and macroscopic realms. At the everyday scale, we can easily grasp the idea of an object needing a certain amount of energy to surmount a barrier. But in the quantum world, particles behave in ways that don't follow these classical rules, leading to surprising phenomena like tunneling. It's a reminder that our intuitions, developed in the macroscopic world, don't always apply when we enter the quantum realm, where the laws of physics take on a completely different character. In summary, quantum tunneling is a phenomenon that showcases the strangeness and beauty of quantum mechanics, where particles can sometimes bypass obstacles that, according to classical physics, should be insurmountable. From the fusion that powers stars to the microscopic precision of scanning tunneling microscopes, tunneling is a vital and ubiquitous process in the universe. It challenges our understanding of reality and reinforces the idea that, at the quantum level, the universe is governed by probabilities, uncertainties, and a set of rules that are vastly different from our everyday experiences. Even as we explore the quantum world, quantum tunneling continues to shape our understanding of nature, revealing just how much we still have to learn about the deepest workings of the universe. Quantum field theory. Imagine standing in the middle of a vast, empty field. The ground beneath you feels solid, yet in the world of quantum mechanics, this field is alive with invisible activity. It's not an ordinary field, but rather a quantum field, a concept that forms the cornerstone of one of the most powerful theories in modern physics, quantum field theory, QFT. At first, it may seem counterintuitive to think of empty space as being full of energy, but in QFT, this seemingly empty vacuum is a dynamic, bustling realm, with particles popping in and out of existence, continuously fluctuating and interacting. In everyday life, we tend to think of particles as individual, well-defined objects, like marbles rolling around in a box. However, quantum field theory suggests something far more profound. Particles are not isolated entities at all. Instead, they are manifestations of underlying fields that permeate the entire universe. These fields are the true fundamental constituents of reality, and everything we observe as particles, electrons, photons, quarks, and more, are merely excitations or ripples in these fields. Let's take a step back and explore the core idea of quantum fields. Picture the surface of a pond. When you drop a stone into the water, waves spread out from the point of impact, propagating through the pond. In a similar way, particles, such as electrons, are disturbances in the quantum fields that fill space. Just as the water in the pond doesn't disappear when a wave moves through it, the quantum field remains present even when a particle appears to be in motion or moving. The difference, however, is that in the quantum realm, these waves and ripples can behave in very strange ways, following the rules of quantum mechanics and not the familiar laws of classical physics. Every fundamental particle is associated with a specific quantum field, For example, the electron is a disturbance in the electron field, and photons are ripples in the electromagnetic field. It's important to note that these fields are not located in specific spots, but rather they extend throughout all of space. And when we observe what we interpret as particles, we're simply seeing the effects of the field in a localized region. These particles, while seemingly discrete, are not separate from the field. They are simply its excitations. One of the remarkable implications of this is that quantum fields are the medium through which all interactions occur. In the classical world, forces like gravity and electromagnetism are carried by particles, such as gravitons or photons. In QFT, these forces are seen as exchanges of virtual particles, particles that exist for a brief moment in time and allow forces to propagate across space. For instance, when two electrons repel each other, the electromagnetic force between them is mediated by the exchange of virtual photons. These virtual particles are not directly observable, but they are an essential part of how forces operate in the quantum world. Now, let's dive deeper into the concept of virtual particles, which are at the heart of QFT. Imagine you're standing near a busy street corner. In a crowded area, people are constantly moving around, passing each other, and interacting. These interactions are not always visible, but they're still occurring. In the quantum world, virtual particles behave in a similar way. They are constantly popping in and out of existence, mediating forces between particles and enabling interactions between them. These virtual particles are virtual because they exist only temporarily, and they don't violate any laws of energy conservation. They're fleeting disturbances in the quantum fields that help explain the interactions between fundamental particles. The concept of virtual particles and quantum fields can also help explain phenomena such as vacuum fluctuations. Even in a vacuum where no actual particles seem to exist, there is still activity. The quantum fields fluctuate, creating momentary bursts of energy that can give rise to particle-antiparticle pairs. These pairs can appear out of nowhere, exist for a brief moment, and then annihilate each other, returning the energy to the field. This is known as vacuum polarization, and while it sounds like a violation of the principle of energy conservation, it's actually allowed by Heisenberg's uncertainty principle, which dictates that energy can be borrowed from the vacuum as long as it's returned quickly enough. This phenomenon, where the vacuum itself is not empty, but full of activity, is a key feature of quantum field theory. In fact, the idea that the vacuum is not empty, but rather teeming with virtual particles, has led to some groundbreaking discoveries in physics, such as the Casimir effect. The Casimir effect refers to the attractive force between two uncharged conducting plates placed close together in a vacuum. This force arises from the fluctuations of the quantum fields in the vacuum, and it demonstrates just how profoundly the vacuum is not empty, but instead an active, energetic field. Quantum field theory doesn't only work for particles that we observe in our daily lives, such as electrons or quarks. It also accounts for the behavior of fields that govern the fundamental forces of nature. The electromagnetic force, for example, is mediated by the photon, and the strong nuclear force is mediated by gluons. The weak nuclear force is mediated by W and Z bosons, and gravity, though not yet fully incorporated into the framework of quantum field theory, is believed to be mediated by gravitons. All these forces arise from the exchange of virtual particles, and all of them can be described as interactions between the fundamental quantum fields. What makes QFT even more remarkable is that it seamlessly combines two pillars of modern physics: quantum mechanics and special relativity. Quantum mechanics governs the microscopic world of particles and wave functions, while special relativity deals with the behavior of objects at high velocities, close to the speed of light. For many years, physicists struggled to reconcile these two theories, but quantum field theory provides a framework that does so elegantly. In QFT, particles are treated as excitations in quantum fields, and these fields obey the principles of special relativity. meaning that the theory works even at velocities approaching the speed of light. This marriage of quantum mechanics and special relativity is a key feature that makes QFT such a powerful theory. One of the most famous successes of QFT is the Standard Model of Particle Physics, which is the theory that describes the electromagnetic, weak, and strong nuclear forces. The Standard Model successfully explains the behavior of subatomic particles and the interactions between them, and it has been confirmed by numerous experiments, including those conducted at particle accelerators like CERN's Large Hadron Collider. In this model, particles like quarks, electrons, and neutrinos are treated as excitations in their respective fields, and the forces between these particles are mediated by the exchange of virtual particles. The discovery of the Higgs boson, a particle that gives other particles mass, was a key triumph of the Standard Model and an experimental confirmation of the ideas of quantum field theory. Despite its success, quantum field theory is still an area of intense research and development, particularly when it comes to the unification of the four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. While QFT has successfully unified the electromagnetic, weak, and strong forces, gravity has not yet been integrated into this framework. The search for a quantum theory of gravity remains one of the greatest challenges in physics. Ideas like string theory and loop quantum gravity are attempts to bridge this gap, but a complete theory of quantum gravity remains elusive. Quantum field theory also raises profound questions about the nature of space, time, and reality. If space is filled with quantum fields and particles are just excitations of those fields, then what exactly is the nature of empty space? Is it truly empty, or is it just full of unseen fields, continuously fluctuating and interacting in ways that we don't yet fully understand? These questions are at the frontier of theoretical physics, and they challenge our deepest intuitions about the nature of the universe. In conclusion, quantum field theory is a revolutionary framework that has reshaped our understanding of the universe. By recognizing that particles are not isolated objects, but rather excitations in quantum fields that permeate all of space, QFT offers a more unified and elegant picture of the fundamental forces and particles of nature. From explaining the forces that govern the behavior of particles to predicting the behavior of quantum fields in a vacuum, QFT has provided some of the most important insights in modern physics. And while there are still mysteries to uncover, particularly in the quest to integrate gravity, quantum field theory remains one of the most profound and successful theories in the history of science. Special relativity. Picture yourself on a train, speeding down the tracks, and you look out the window. The scenery flies by, and you feel the smooth motion of the train beneath you. Everything feels normal, and the laws of physics seem to behave exactly as you expect. However, if someone outside the train were to observe you, the situation might seem entirely different. To them, you're moving at an incredible speed, racing past them at the speed of the train. But to you sitting in the train, everything feels still and consistent. This fundamental observation, the difference in how we experience motion depending on our frame of reference, lies at the heart of Albert Einstein's theory of special relativity. Special relativity, one of the most revolutionary ideas in physics, fundamentally altered our understanding of space and time. In its simplest form, the theory tells us that the laws of physics are the same for all observers, regardless of how fast they are moving, as long as they are not accelerating. That may sound simple, but the consequences are anything but. Special relativity shows that space and time are not absolute and unchanging, as we once thought, but instead are intertwined and flexible, stretching and contracting in ways that we can only fully understand in the extreme conditions of high-speed motion. One of the key insights of special relativity is that the speed of light is always constant, no matter how fast you're moving. This is a profound departure from the way we think about the world around us. Imagine you're in a spaceship traveling through space. If you shine a flashlight forward and someone else is in a spaceship traveling in the opposite direction, they might think that your flashlight beam is moving away from them faster than the speed of light, right? But according to Einstein, that's not the case. Whether you're speeding toward the other spaceship or moving away from it, the speed of the light beam remains the same to both of you. It's always 186,282 miles per second, regardless of your motion or theirs. This constancy of the speed of light is the cornerstone of special relativity and leads to some of the theory's most counterintuitive results. To understand this, let's dive deeper into the idea that space and time are not fixed, but malleable. According to special relativity, space and time are not separate entities, but are part of a single unified framework known as space-time. Imagine a fabric that stretches across the universe. This is space-time. When objects with mass move through space, they bend and distort this fabric. The faster an object moves, the more it warps space-time around it. This is where things start to get strange. As you move faster, closer to the speed of light, time itself begins to slow down for you relative to someone who's standing still. Similarly, the space you're moving through starts to contract in the direction of motion. This is known as time dilation and length contraction, two of the most important and mind-bending consequences of special relativity. Let's start with time dilation. If you're in a spaceship traveling at a speed close to the speed of light, time for you will pass more slowly compared to someone who is at rest on Earth. This phenomenon has been experimentally confirmed in a number of ways, including with precise atomic clocks flown on airplanes or satellites. For example, if an astronaut were to travel at nearly the speed of light for several years and then return to Earth, they would find that much more time had passed for people back home. They might have aged only a few years, but decades could have passed for the people who remained on Earth. This slowing down of time becomes more pronounced the faster you move, and as you approach the speed of light, time effectively comes to a standstill. This idea is difficult to grasp because our everyday experience tells us that time always moves forward at the same rate. However, in the strange world of special relativity, time itself is no longer a constant. It depends on your motion, and it can stretch or shrink depending on how fast you're traveling. But this doesn't mean that time is faster or slower in some absolute sense, only that time is experienced differently for observers in different states of motion. This is a fundamental shift in how we think about the passage of time, and it opens the door to some very strange possibilities. Next, let's explore length contraction, the second major consequence of special relativity. Just as time can slow down, distances in the direction of motion contract as you approach the speed of light. For example, if you're moving at a significant fraction of the speed of light, the length of your spaceship would appear to shrink from the perspective of someone observing from outside the spaceship. This contraction happens only in the direction of motion. The spaceship would appear to be shorter, but its width and height would remain unchanged. It's important to note that this length contraction is not an optical illusion or a trick of the eye. It's a real effect predicted by the theory of special relativity, and it occurs because space itself is being stretched and compressed in different ways for different observers. But how can these seemingly impossible ideas be true? After all, we experience the world as if time flows steadily and distances remain constant. To answer this, we need to rethink the way we understand space and time. In the Newtonian view of the universe, space and time were absolute. No matter how fast you were moving, space and time were the same for everyone. But in the relativistic view, space and time are intertwined, forming a single, four-dimensional fabric that can bend, stretch, and warp depending on the motion of objects. This interconnectedness of space and time leads to the strange effects of time dilation and length contraction. It's not that time slows down or space shrinks in an absolute sense, it's that they're relative to your speed, and the faster you move, the more the fabric of space-time warps around you. The idea of space-time itself being flexible and relative is a dramatic departure from our intuitive understanding of the world. But it has been experimentally confirmed in many ways, including with particles that travel close to the speed of light, such as those in particle accelerators. For example, high-energy particles called muons are created in the atmosphere when cosmic rays strike the Earth. These muons travel toward the surface of the planet, and because they move so quickly, their internal clocks tick more slowly than the clocks of stationary observers on the Earth's surface. As a result, the muons live longer than they would if they were at rest, and they can reach the Earth's surface before decaying. This is a direct consequence of time dilation, and it has been measured experimentally, confirming the predictions of special relativity. But perhaps the most striking implication of special relativity is the idea that nothing can travel faster than the speed of light. According to Einstein, as you approach the speed of light, the energy required to continue accelerating increases without bound. In other words, it would take an infinite amount of energy to push an object to the speed of light, making it impossible to reach that limit. This leads to the conclusion that the speed of light is an unattainable upper bound for motion in the universe. This has profound consequences for the way we think about travel, communication, and causality. It implies that information or objects cannot be transmitted faster than light, which places strict limits on the speed at which we can explore the universe or communicate over vast distances. Despite its seemingly strange predictions, special relativity has stood the test of time and experimental verification. It has become one of the most well-established theories in physics, forming the foundation for much of modern physics, including the theory of general relativity and even technologies like GPS. And yet, despite its success, the ideas it presents remain deeply counterintuitive and challenge our everyday experiences. The theory forces us to rethink the very nature of space, time, and motion, and its effects are most dramatically seen in the extreme, high-speed environments that exist far beyond our daily lives. But even in our ordinary world, the ideas of special relativity subtly shape the behavior of the universe, and its impact continues to reverberate through the fabric of modern physics. General relativity. Imagine you're standing on the surface of a vast, empty plain, surrounded by flat, unyielding ground stretching in all directions. The sun rises high in the sky, its warmth and light pouring down evenly. Now, picture someone coming up to this plain and setting a heavy object in the middle of it, a massive boulder. As it settles onto the ground, the surface begins to curve and warp slightly around the boulder. The once flat ground begins to bend and distort, forming a dip, almost like a trampoline beneath it. This curvature of the ground is analogous to the curvature of space and time described by Einstein's theory of general relativity, a theory that fundamentally redefines our understanding of gravity, space, and time itself. Before Albert Einstein developed general relativity, gravity was understood through the lens of Sir Isaac Newton's theory. According to Newton, gravity was a force that acted instantaneously at a distance, like a magnetic pull between objects. If you had two objects, such as the Earth and a falling apple, gravity would instantly pull the apple toward the Earth. This model worked very well for everyday objects moving slowly compared to the speed of light. However, when scientists observed stars, planets, and galaxies moving at near-light speeds, Newton's model began to break down. That's when Einstein came into the picture, revolutionizing our understanding of gravity with his theory of general relativity. Einstein's idea was audacious. Instead of treating gravity as a force that acted between masses, he proposed that gravity was a distortion or curvature in space-time itself. In essence, he argued that mass and energy bend and curve space-time around them, and this curvature dictates the motion of objects within that space-time. Imagine space-time as a flexible, stretchy fabric. Mass and energy bend this fabric in response to their presence. Objects like planets, stars, and even light bend and curve the fabric of space-time as they move through it. To help us understand this concept, Einstein used the analogy of a trampoline. Imagine stretching a large, heavy trampoline across a room. Now, place a heavy ball, representing, say, the Earth, at the center of the trampoline. The fabric of the trampoline will curve around the ball, forming a depression. If you roll a marble across the trampoline's surface, it will follow the curve, moving toward the center of the depression. Similarly, massive objects like the Sun curve space-time, causing objects like planets and light to follow curved paths through space and time. This is gravity, according to general relativity. One of the most famous predictions of general relativity is that massive objects like the Sun can bend the light that passes by them. This bending effect is known as gravitational lensing. Imagine starlight traveling toward Earth. As it approaches the massive mass of the Sun, space-time around it curves, and the light bends, causing distant stars to appear slightly distorted or shifted from their true position. This bending of light has been observed repeatedly in astronomical observations, both from the ground and from space, and it has confirmed Einstein's theory of general relativity beyond any reasonable doubt. The most dramatic consequence of general relativity is that gravity can bend space-time to such an extreme degree that it can bend light, alter our perception of time, and even warp space itself. One of the most famous examples of this is the phenomenon of black holes. A black hole is the result of a collapsed star whose gravitational field is so intense that not even light can escape it. According to general relativity, when a massive star reaches the end of its life cycle, it can collapse into a point where space-time curves infinitely. This point is called a singularity. At this singularity, space-time itself becomes infinitely warped, and gravity becomes infinitely intense. Anything that crosses the event horizon, the point of no return, of a black hole cannot escape its gravitational grip, not even light. As a result, light and other forms of electromagnetic radiation are bent around the edge of the black hole, creating a visible boundary known as the event horizon. Einstein's theory predicted black holes long before they were observed. It wasn't until 2019 that scientists captured the first image of a black hole, a supermassive one at the center of the galaxy M87. The image showed a dark circular shadow against a backdrop of glowing light, with a clear ring around the edge. This was the event horizon. The light surrounding this ring was bent and twisted by the intense gravitational pull of the black hole, perfectly matching Einstein's predictions. This landmark observation was a triumph for general relativity and confirmed the existence of black holes as predicted. Another key aspect of general relativity is the concept of space-time itself. Space-time is not just the fabric of space in which we exist, it's also how we understand time. In Einstein's theory, time and space are interconnected in a way that is difficult for us to visualize. For example, if you were to climb into a spacecraft and travel close to the speed of light, time would behave differently for you compared to someone who stays on Earth. According to general relativity, the faster you move, the slower time runs. This effect has been demonstrated with precision through experiments such as those involving fast-moving particles in particle accelerators, or highly accurate atomic clocks flown on jets. These experiments show that time truly is relative, just as space is, and it can stretch or contract depending on your speed and the strength of gravity around you. One striking consequence of general relativity's view of space-time is that it allows for the existence of time dilation. Time dilation means that time can move differently in different frames of reference. If you were orbiting Earth in a highly sensitive satellite, time would move slightly faster for you compared to someone standing on the surface of Earth. This effect has profound implications for our understanding of the universe, including satellite navigation systems like GPS. Without accounting for time dilation, these systems would become less accurate over time. Finally, general relativity has given us insight into some of the most mysterious phenomena in the universe, such as gravitational waves. These ripples in space-time are caused by catastrophic events like colliding black holes or neutron stars. Einstein's theory predicted these waves long before they were detected, and the first experimental observation came in 2015. Gravitational waves carry information about the violent events that create them and have since been used to study collisions between black holes, the expansion of the universe, and other extreme phenomena. General relativity fundamentally changed our understanding of gravity, space, and time. It showed that these concepts are not fixed, immutable forces acting at a distance. Instead, they are interconnected, dynamic features of space-time itself. Space-time is a flexible, evolving entity that can bend, stretch, twist, and ripple depending on the presence of mass and energy. This flexibility opens up new ways of thinking about the universe, from black holes and cosmic expansion to time dilation and gravitational waves. General relativity doesn't just describe how gravity works, it reshapes our understanding of the universe on its deepest level. It forces us to rethink what we mean by space, time, and gravity itself, opening up a realm of wonder and discovery that continues to challenge and expand the human mind. Gravitational waves. You are standing by a calm pond. The water is perfectly still, reflecting the blue sky above. But then, a stone is thrown into the water, causing ripples to spread across the surface. These ripples move outward, distorting the smooth surface of the pond as they propagate. Now, picture that instead of a stone, it's something far more massive, like a collision of two black holes or the explosion of a supernova. And instead of a pond, it's the fabric of space-time itself. The ripples created by such cosmic events are called gravitational waves. Gravitational waves are one of the most mind-boggling yet profound predictions of Albert Einstein's theory of general relativity, and they reveal an entirely new way of perceiving the universe. In the simplest terms, gravitational waves are ripples in the fabric of space-time that occur whenever massive objects accelerate, causing distortions in the very geometry of space and time. These waves travel at the speed of light, carrying with them information about the most violent and energetic processes in the universe. But the concept of gravitational waves wasn't something that people could simply observe. For many years, the waves were only a theoretical idea. It took nearly a century before scientists had the technology to detect them directly. And when they finally did, it wasn't just a triumph of science. It was a revelation that opened a whole new window into the cosmos. But how did this all come about, and what makes these waves so extraordinary? Let's start with a quick look at the theory behind gravitational waves. According to general relativity, space and time are not separate entities. Instead, they form a unified four-dimensional structure known as space-time. Objects with mass such as stars, planets, and black holes warp space-time around them, much like a heavy ball placed on a rubber sheet causes the sheet to bend. This warping of space-time is what we perceive as gravity. In the case of gravitational waves, massive objects, such as two orbiting black holes, disturb the fabric of space-time, creating ripples that spread outward. These ripples, like the waves in the pond, oscillate in and out as they move, stretching and compressing space-time along their path. When they reach us here on Earth, they can cause minuscule changes in the distance between objects. In theory, even the most sensitive instruments wouldn't be able to detect gravitational waves unless they were caused by incredibly violent events like the collision of two supermassive black holes or the merging of neutron stars. The idea of gravitational waves was first proposed by Einstein in 1915 as part of his general theory of relativity. He realized that accelerating massive objects, like two orbiting stars, would not just warp space-time but could send out waves of distortion through the fabric of space-time itself. However, Einstein initially thought that these waves would be so faint and difficult to detect that they might never be observed. For many decades, gravitational waves remained a purely theoretical concept. That all changed in 2015 when scientists working with the Laser Interferometer Gravitational Wave Observatory, LIGO, made an astonishing announcement. They had detected gravitational waves for the first time. These waves came from the collision of two black holes, which were about 1.3 billion light-years away. The signal, picked up by LIGO's ultra-sensitive detectors, was unmistakable. It was the sound of space-time itself being disturbed by one of the most cataclysmic events in the universe, the merger of two black holes. This groundbreaking discovery confirmed one of the key predictions of general relativity and opened up a whole new branch of astrophysics. But what exactly happens during a gravitational wave event? When two black holes, or other extremely dense objects, begin to orbit each other, they cause ripples in spacetime. As the black holes spiral closer together, these ripples become stronger, much like the waves in the pond get bigger as the stone sinks deeper into the water. When the black holes eventually merge, the resulting burst of energy sends gravitational waves through space. These waves carry information about the masses and spins of the black holes, as well as the nature of the collision itself. The waves themselves are incredibly faint by the time they reach Earth, meaning that detecting them requires extremely sensitive equipment. LIGO's detectors work by using laser interferometry, where two laser beams are split and sent down long arms in perpendicular directions. When a gravitational wave passes through the detector, it stretches and compresses space-time, causing a tiny change in the distance between the laser beams. This change is incredibly small, on the order of 1/10,000th the diameter of a proton, but it can be detected with astonishing precision. In the case of the 2015 detection, the signal from the black hole merger lasted only a fraction of a second, but in that brief moment, it provided a wealth of information about the event. The discovery was not only a triumph of science, but also a testament to human ingenuity, as it was the result of decades of work from thousands of scientists and engineers. Gravitational waves don't just provide us with information about black holes, they also offer us a glimpse into the early universe. For example, the detection of gravitational waves could potentially help us learn about the formation of the first stars and galaxies. By studying the characteristics of these waves, scientists can gain insight into the most extreme environments in the universe, including the interior of neutron stars and the physics of black hole mergers. But why are gravitational waves so important? What makes them so special? The key lies in the fact that they carry information that is impossible to get through other means. For example, light, whether visible, ultraviolet, or infrared, can be blocked or distorted by dust and gas in space, which makes it difficult to study certain astronomical objects. Gravitational waves, on the other hand, can pass through anything. This makes them an incredibly powerful tool for astronomers, allowing us to study the universe in a way that was once unimaginable. The 2015 detection of gravitational waves marked the beginning of a new era of astronomy. Since then, LIGO and its counterpart, Virgo, have made several other groundbreaking detections, including the collision of neutron stars, which also sent out gravitational waves. These detections have provided an entirely new perspective on some of the universe's most violent events, and they promise to reveal even more in the years to come. But as we explore the potential of gravitational waves, we must also acknowledge the immense challenges involved in their detection. The changes in spacetime caused by these waves are infinitesimally small, and the instruments required to measure them are incredibly delicate. LIGO, for example, is designed to detect displacements as small as 1/10,000th the width of a proton. This requires an extraordinary level of precision as well as a sophisticated system of noise reduction to eliminate interference from Earth-based sources like traffic, earthquakes, and even the movement of air molecules. Despite these challenges, the ability to detect gravitational waves has opened up a new chapter in our understanding of the universe. It has given us a tool to observe the most extreme phenomena, from the collision of black holes to the merging of neutron stars. Each detection provides more data about the cosmos and helps us refine our theories of gravity, space, and time. The discovery of gravitational waves is a reminder that the universe is far more dynamic, far more mysterious than we could have ever imagined. It is a testament to human curiosity, ingenuity, and the relentless pursuit of knowledge. And as we continue to study these ripples in space-time, we will undoubtedly uncover new truths about the fabric of the universe itself. Truths that have been hidden from us for eons, waiting to be revealed by the waves of the cosmos. Black hole physics. Suppose a point in space where the rules we know about the universe no longer apply, where the forces of nature converge in such a way that they break down. At the center of every black hole lies this mysterious place, known as the singularity, where gravity is so intense that space-time itself warps and crumples. This is where black hole physics begins, a field of study that pushes our understanding of the universe to its most extreme boundaries. The concept of a black hole can be traced back to the 18th century, but it wasn't until Albert Einstein's theory of general relativity in the early 20th century that we began to understand how these strange objects could form and behave. General relativity predicts that a massive object, when it collapses under its own gravity, can create a black hole, a region in space where gravity is so strong that not even light can escape. Once you pass the event horizon, the point of no return, you can never escape. The physics of black holes is anything but simple, yet understanding them is crucial to understanding the universe itself. Black holes are places where the fabric of space-time is stretched to its limits, and they provide a testing ground for theories of gravity, quantum mechanics, and thermodynamics. In fact, black holes are one of the best places to explore the limits of our knowledge. The key to understanding black holes lies in the first law of their existence, the escape velocity. Everything in the universe has a gravitational pull, which means that objects are attracted to one another. Normally, this force is relatively weak, so we don't notice it in our everyday lives. But if an object has a very large mass, it will exert a stronger gravitational force. The escape velocity is the speed that an object must travel in order to escape the gravitational pull of a massive body. For most objects in the universe, the escape velocity is relatively low. But as an object's mass becomes denser and denser, the escape velocity becomes higher and higher. For a black hole, this escape velocity reaches the speed of light itself, meaning that nothing, not even light, can escape. This is why black holes are invisible to our eyes. They don't emit light, nor do they reflect it. Instead, they only reveal themselves through their interactions with nearby matter. The point of no return for a black hole is called the event horizon. It's the boundary around a black hole, beyond which nothing can escape. If you were to fall into a black hole, you would pass through the event horizon and be pulled toward the singularity at its center. As you fall in, time itself would appear to slow down due to the extreme warping of space-time, and from the outside observer's perspective, you would appear to freeze in time at the event horizon. This brings us to another curious feature of black holes, the paradox of time. The closer you get to a black hole, the more intense the gravitational field becomes, and this leads to a phenomenon known as time dilation. As you approach the event horizon, time appears to slow down relative to someone observing you from afar. From your own perspective, however, time would continue to move forward normally. But for someone watching from the outside, it would appear as though you're slowly frozen in time. At the center of the black hole lies the singularity, a point where gravity is infinitely strong and space-time becomes infinitely curved. Here, the laws of physics as we know them break down, and no theory currently exists that can fully describe the physics of this extreme environment. What happens inside the singularity remains one of the greatest mysteries in physics. Despite the singularity's mind-bending properties, black holes have another fascinating feature. They can be studied through the behavior of matter around them. Although we can't directly observe the inside of a black hole, we can study the matter swirling around it as it falls into the event horizon. This material, often in the form of gas and dust, forms an accretion disk that heats up to incredibly high temperatures as it spirals inward, emitting X-rays and other forms of radiation. This radiation allows us to detect and study black holes from a distance. Interestingly, black holes don't just suck up matter like a cosmic vacuum cleaner. In fact, many black holes are thought to play an important role in shaping galaxies and the larger structure of the universe. As matter falls into a black hole, it can release enormous amounts of energy, which can affect the surrounding space. For example, the supermassive black hole at the center of our Milky Way galaxy is thought to be responsible for powering some of the most energetic phenomena in the universe, including quasars, extremely bright and distant objects that emit vast amounts of radiation. Black holes also provide us with insights into one of the biggest puzzles in modern physics, the unification of general relativity and quantum mechanics. General relativity describes the behavior of massive objects and the curvature of space-time, while quantum mechanics deals with the behavior of particles on the smallest scales. These two theories are incredibly successful in their respective domains, but they seem to contradict each other when it comes to the extreme conditions inside a black hole. The singularity, for instance, is a place where both the effects of gravity and quantum mechanics are at their most extreme. Understanding the physics of black holes could therefore help us unlock a theory of quantum gravity, one of the holy grails of modern physics. One of the most remarkable developments in black hole physics came from Stephen Hawking, who in 1974 made a groundbreaking discovery about the thermodynamics of black holes. Hawking proposed that black holes are not completely black, but instead emit radiation, now known as Hawking radiation. According to quantum mechanics, empty space is not truly empty, but instead teems with virtual particles that constantly pop in and out of existence. Near the event horizon of a black hole, these particles can be separated, with one particle falling into the black hole and the other escaping. The escaping particle is detected as radiation, which over time causes the black hole to slowly lose mass and energy. This means that black holes can eventually evaporate, albeit over incredibly long periods of time. Hawking's discovery was revolutionary because it suggested that black holes could have a finite lifetime and that they could eventually die by radiating away their mass. This idea raised further questions about the nature of information in the universe. If a black hole evaporates completely, what happens to the information contained within it? This is known as the black hole information paradox, and it remains one of the most debated topics in theoretical physics. The resolution of this paradox could have profound implications for our understanding of both quantum mechanics and the nature of reality itself. Despite these groundbreaking discoveries, many mysteries remain about black holes. For example, we still don't fully understand what happens at the singularity, or how to reconcile the quantum mechanical and relativistic descriptions of black holes. But one thing is certain: black holes are some of the most fascinating and enigmatic objects in the universe. They challenge our deepest assumptions about space, time, and the nature of the cosmos, and studying them will likely continue to push the boundaries of human knowledge for years to come. Event horizon. The event horizon of a black hole is one of the most intriguing and enigmatic features in the universe. It marks the point of no return, the boundary beyond which nothing can escape the overwhelming pull of gravity, not even light. Yet, despite its critical role in understanding black holes and the nature of space-time, the event horizon remains an elusive concept, one that challenges our intuition and invites a deeper look into the fabric of the universe itself. At its core, the event horizon is a boundary, not a physical surface like the surface of a planet or a star, but a threshold in space-time that signifies the limit beyond which escape from the black hole is impossible. This boundary is linked to the properties of the black hole itself. The event horizon's defining characteristic is that the escape velocity at this point exceeds the speed of light, meaning that even light itself, which travels at approximately 300,000 kilometers per second, cannot escape from within the event horizon. Once something crosses this threshold, it is inexorably drawn into the singularity at the center of the black hole, where space-time curvature becomes infinite. To understand the event horizon more fully, let's break it down. The concept of gravity, which governs how objects interact in space, becomes extreme in the vicinity of a black hole. In fact, a black hole is formed when a star of significant mass collapses under its own gravity. When this collapse occurs, the core of the star is crushed to a point of infinite density, and the gravitational pull in that area becomes so strong that it distorts the very fabric of space and time. The event horizon is the boundary at which this intense gravity makes it impossible for any object or signal to escape once it has crossed. This concept can be likened to the edge of a waterfall. Imagine standing at the precipice of a waterfall. As you approach the edge, you can feel the current pushing you forward. At this point, you could turn back and walk away, resisting the force. But once you step over the edge, gravity takes over, and you are carried down the waterfall, unable to return. The event horizon operates in a similar way. Once you cross the event horizon, the black hole's pull becomes so strong that there's no way to move away from it. No force, not even light, can overcome this pull and escape. The event horizon's connection to time and space adds another layer of complexity to our understanding. According to Einstein's theory of general relativity, the presence of massive objects distorts the fabric of space-time, and the more massive an object, the greater its distortion. Black holes, being incredibly dense and compact, warp space-time to such an extreme degree that the normal rules of physics seem to break down. The event horizon marks the boundary where this distortion becomes so severe that time, space, and the very laws of physics behave in ways that are beyond our ordinary experience. One of the most mind-bending implications of the event horizon is that from the perspective of an outside observer, time appears to slow down as an object approaches the event horizon. To an outside observer, an object falling toward the black hole seems to slow down more and more as it gets closer to the event horizon, ultimately appearing to freeze in place just before crossing the threshold. However, from the perspective of the object itself, it crosses the event horizon without noticing any unusual change in its experience of time. This difference arises from the warped nature of space-time near a black hole. It's important to note that the event horizon is not a fixed, solid boundary. Its size depends on the mass of the black hole. A more massive black hole has a larger event horizon, while a smaller black hole has a smaller one. This size is referred to as the Schwarzschild radius, named after the physicist Karl Schwarzschild, who first derived the solution to the equations of general relativity that describe black holes. The Schwarzschild radius is directly proportional to the mass of the black hole, and it marks the critical distance from the singularity where the escape velocity becomes greater than the speed of light. As fascinating as the event horizon is, it's important to remember that the event horizon is not an absolute edge in the traditional sense. It does not mark a hard, tangible surface that an object would crash into. Rather, it represents a threshold in space-time that separates the observable universe from the hidden interior of the black hole. Beyond the event horizon, information becomes inaccessible to external observers. This means that once something crosses this boundary, it is essentially cut off from the rest of the universe, and any information about it is lost. This brings us to one of the most famous paradoxes in physics, the black hole information paradox. The paradox arises from the fact that quantum mechanics, the theory that governs the behavior of subatomic particles, suggests that information can never be truly lost. However, when something crosses the event horizon, it seems that all information about that object is destroyed, creating a conflict between the principles of quantum mechanics and general relativity. This paradox has sparked decades of debate among physicists, and while there is no consensus yet on how to resolve it, one proposed solution involves the idea of information scrambling at the event horizon. This theory suggests that information is not lost, but rather becomes encoded in the black hole's quantum state in a highly scrambled form, which may eventually be recoverable. The event horizon is not just a theoretical concept. In 2019, the Event Horizon Telescope, EHT, collaboration, made history by capturing the first-ever image of a black hole's event horizon. Using a network of radio telescopes spread across the globe, scientists were able to observe the supermassive black hole at the center of the galaxy M87. The resulting image revealed a bright ring of light surrounding a dark center, what appeared to be the shadow of the event horizon. This image confirmed many predictions of general relativity and marked a major milestone in our understanding of black holes. In addition to its role in black holes, the event horizon also plays a crucial part in the broader study of the nature of the universe. Black holes and the event horizons that define them are laboratories for testing the limits of physics. They challenge our understanding of space-time, gravity, and the nature of information itself. By studying the behavior of objects near the event horizon, scientists hope to uncover new insights into the fundamental workings of the universe, including the potential reconciliation of quantum mechanics and general relativity. The study of event horizons also offers a glimpse into the ultimate fate of the universe. In the far future, as galaxies continue to move away from each other in the expanding universe, distant objects will eventually pass beyond the event horizon of the universe itself. In this scenario, the entire universe would appear as a black hole to any distant observer, and no information from the outside universe would ever be able to reach those inside. This cosmic event horizon would mark the final boundary in space-time, where no light or matter could ever escape. The event horizon is a powerful symbol of the limits of human knowledge and understanding. It represents a threshold beyond which we cannot see, hear, or understand. It reminds us that there are parts of the universe that remain forever hidden, beyond the reach of even our most sophisticated scientific instruments. Yet, paradoxically, the study of event horizons brings us closer to understanding the deepest mysteries of the cosmos. By probing the edges of black holes and the nature of space-time, we gain insights into the very structure of reality itself. The event horizon, in all its elusive mystery, challenges our preconceptions about the universe and invites us to embrace the unknown. It is a symbol of the frontier of science, where our understanding meets the boundaries of the unobservable, and where new discoveries await. Hawking radiation. Hawking radiation is one of the most profound and paradoxical predictions in modern physics, offering a glimpse into the strange behavior of black holes and their relationship with the quantum world. At first glance, the idea that black holes, objects famous for trapping everything within their grasp, including light, might actually emit radiation seems absurd. Yet this idea has become a cornerstone of theoretical physics, revealing the interconnectedness of quantum mechanics, general relativity, and the nature of the universe itself. In 1974, the British theoretical physicist Stephen Hawking proposed that black holes are not completely black after all. Instead, they emit radiation due to quantum effects near the event horizon, the boundary beyond which nothing can escape. This radiation, now known as Hawking radiation, arises from the bizarre behavior of particles in the vacuum of space-time near the black hole's event horizon. To understand Hawking radiation, it helps to start with a basic idea from quantum mechanics, the concept of the vacuum. In classical physics, we think of the vacuum as empty space, an absence of matter and energy. However, in quantum mechanics, the vacuum is never truly empty. It is filled with fleeting particles that spontaneously pop into existence and then annihilate each other in a fraction of a second. These virtual particles exist because of the uncertainty principle, which allows energy fluctuations to occur, even in what we perceive as empty space. Now, imagine this happening near the event horizon of a black hole, the point beyond which not even light can escape. According to quantum field theory, pairs of virtual particles, one positive and one negative, constantly appear and disappear, annihilating each other almost instantly. However, when this process occurs right at the event horizon, something extraordinary happens. The intense gravitational field of the black hole can pull these virtual particles apart before they have a chance to annihilate each other. One particle falls into the black hole, while the other escapes into space. From an external observer's perspective, it looks as though the black hole is emitting radiation. The escaping particle, which has positive energy, is free to move away, while the particle that falls into the black hole carries negative energy, which reduces the black hole's mass. This is the essence of Hawking radiation, particles being emitted by the black hole due to quantum effects at the event horizon. Hawking's insight was groundbreaking because it introduced the idea that black holes could slowly lose mass over time. This process of radiation emission would cause a black hole to shrink and eventually evaporate. If this radiation continues long enough, a black hole might lose enough mass that it vanishes completely, leaving behind nothing but the radiation itself. The concept of black hole evaporation challenges the traditional view that black holes are permanent fixtures in the universe, offering a new perspective on the ultimate fate of these mysterious objects. To grasp the significance of this idea, it helps to think of it in terms of energy conservation. Normally, when particles pop into and out of existence, they do so in pairs, one particle of positive energy and one of negative energy. Together, these particles balance each other out, and no net energy is gained or lost. However, when one of these particles falls into a black hole, it carries negative energy, effectively reducing the total energy and mass of the black hole. The particle that escapes carries positive energy, which we observe as radiation. Over time, this process causes the black hole to lose mass, which is the key to the concept of black hole evaporation. The idea that black holes can shrink and eventually disappear due to the emission of Hawking radiation has profound implications. It suggests that the universe may not be populated with eternal black holes, as was once believed. Instead, even the most massive black holes could, in theory, eventually evaporate and vanish, leaving behind only a faint trace of radiation. However, despite its theoretical foundation, Hawking radiation has not yet been observed directly. The difficulty of detecting Hawking radiation stems from the fact that it is incredibly weak and faint, particularly for large black holes. The radiation emitted by a stellar mass black hole would be so faint that it would be nearly impossible to detect with current technology. On the other hand, tiny primordial black holes, which are much smaller and would have much stronger radiation, may have evaporated completely by now, making them impossible to detect as well. Nevertheless, the theory of Hawking radiation remains important because it has profound implications for the nature of information and the fundamental laws of physics. One of the most intriguing aspects of black hole evaporation is its connection to the black hole information paradox, a puzzle that has perplexed physicists for decades. According to quantum mechanics, information about the state of a system should never be lost. However, if a black hole evaporates completely, what happens to the information that fell into it? Hawking radiation presents a dilemma. The radiation that escapes from the black hole is random and carries no information about the object that fell in. This would seem to violate the principle of information conservation in quantum mechanics, leading to the black hole information paradox. Some physicists believe that the resolution to this paradox lies in the nature of the Hawking radiation itself. One possible solution is that the information about the objects that fall into a black hole is not lost, but rather encoded in the radiation emitted by the black hole in a highly scrambled form. This idea, known as the soft hair theory, suggests that black holes may carry more information than we once thought, and that this information could be encoded in subtle correlations within the Hawking radiation. If this turns out to be true, it could resolve the information paradox and provide a deeper understanding of the relationship between quantum mechanics and gravity. Moreover, the study of Hawking radiation provides insight into the fundamental structure of space-time and the nature of quantum gravity. The process of black hole evaporation may ultimately reveal new physics, offering a window into the unification of quantum mechanics and general relativity. This is a major area of research in theoretical physics as scientists strive to understand how gravity, which governs the behavior of large objects, can be reconciled with quantum mechanics, which governs the behavior of subatomic particles. Hawking radiation also has implications for cosmology and the ultimate fate of the universe. If black holes can evaporate, then the universe might one day be completely devoid of them, leaving only the radiation they emitted behind. This could mean that the universe in the far future will be a very different place, a universe without the massive objects that have shaped its history. Some theories suggest that the remnants of black holes, once evaporated, might leave behind tiny Planck mass particles or other exotic objects that could play a role in the next phase of cosmic evolution. Even though we have yet to directly observe Hawking radiation, it is a powerful theoretical concept that has reshaped our understanding of black holes, the nature of information, and the fundamental laws of the universe. It represents the intersection of quantum mechanics, general relativity, and thermodynamics, providing a tantalizing glimpse into the mysterious processes that govern the cosmos. As scientists continue to probe the secrets of black holes and the nature of space-time, Hawking radiation will undoubtedly remain a central concept in the quest to understand the deepest mysteries of the universe. Dark matter. Dark matter is one of the most intriguing and elusive concepts in modern physics, a mysterious substance that makes up roughly 27% of the universe, yet remains completely invisible. It doesn't emit, absorb, or reflect light, which is why it's called dark. Despite its invisibility, dark matter exerts a gravitational pull on ordinary matter, stars, and galaxies, affecting their motions in ways that cannot be explained by the known matter in the universe. In fact, it's the unseen presence of dark matter that keeps galaxies from flying apart at the edges due to their rapid rotation. Without it, our current understanding of the cosmos would crumble. The story of dark matter begins with observations that didn't match up with our expectations. In the 1930s, the Swiss astronomer Fritz Zwicky made an odd discovery while studying the Coma galaxy cluster. He noticed that the galaxies within the cluster were moving far faster than they should be, given the amount of visible matter in the cluster. According to Newtonian gravity, the galaxies should have been flying apart, but they weren't. Zwicky proposed that some unseen force or substance was exerting a gravitational pull, holding the galaxies together. He dubbed this invisible material dark matter, though its true nature remained a mystery. This wasn't the only clue suggesting the presence of dark matter. In the 1970s, the American astronomer Vera Rubin was studying the rotation curves of galaxies, graphs that show the speed of stars at different distances from a galaxy's center. According to Newtonian physics, the stars at the edges of galaxies should be moving slower than those closer to the center, because the visible matter in the galaxy would be concentrated toward the center, creating a weaker gravitational pull at the outer edges. But Rubin found that the stars at the edges of galaxies were moving just as fast as those near the center. This observation suggested that there was more mass than could be accounted for by visible matter, once again pointing to the existence of dark matter. But if dark matter doesn't emit light or interact with electromagnetic forces in any way, how can it be detected? This is where things get interesting. The key to detecting dark matter lies in its gravitational effects on visible matter. We can observe how galaxies, clusters of galaxies, and even the structure of the entire universe behave, and infer the presence of dark matter from these observations. The fact that dark matter can exert gravitational forces but does not interact with light means that it does not fit into our familiar categories of ordinary matter, which includes protons, neutrons, and electrons, particles that make up atoms. So, what exactly is dark matter? To date, we don't know for sure, but there are several leading theories. One of the most popular candidates is a class of particles called WIMPs, or weakly interacting massive particles. These hypothetical particles are thought to have mass, which is why they exert gravity, but they interact with other matter only very weakly, which is why they don't emit or absorb light. WIMPs could be detected by their gravitational effects or possibly through very rare interactions with ordinary matter. Despite extensive efforts to detect them in particle accelerators or underground laboratories, WIMPs have yet to be observed. Another leading candidate is axions, which are much lighter than WIMPs and were proposed as a solution to a different problem in physics known as the strong CP problem. Like WIMPs, axions are weakly interacting and don't emit light, but their properties differ in key ways. Axions, if they exist, would be very low in mass, making them difficult to detect, but their abundance could still explain the gravitational effects we observe in galaxies and clusters. In addition to these particle candidates, there are other theories that involve modifications to our understanding of gravity itself. For example, the MOND, modified Newtonian dynamics, theory posits that the laws of gravity change at very large distances, particularly in the outer regions of galaxies. According to MOND, the apparent need for dark matter could be a result of how gravity behaves at these extreme scales rather than the presence of an unseen substance. However, this theory has yet to provide a comprehensive explanation of all the observations, and most physicists lean toward the idea that dark matter exists as a form of unknown particle rather than a modification of gravity. Dark matter's existence has also been inferred through the study of large-scale structures in the universe. The cosmic web, the vast network of galaxies, clusters, and filaments that make up the structure of the universe, could not have formed the way it did without dark matter. In the early universe, dark matter's gravitational influence helped to pull ordinary matter together, forming the first galaxies and clusters. Without this unseen mass, the formation of galaxies would have been much slower, and the universe would look very different today. One of the most compelling pieces of evidence for dark matter comes from gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. When light from a distant object, such as a galaxy or a star, passes near a massive object, its path is bent by the gravitational field of that object. This bending of light is known as gravitational lensing, and it can be used to map the distribution of mass in the universe, even when that mass is invisible. Studies of gravitational lensing have revealed that there is much more mass in galaxy clusters than can be accounted for by visible matter alone, further confirming the presence of dark matter. Despite its gravitational influence, dark matter does not interact with electromagnetic forces, which is why it cannot be detected by conventional telescopes. We can't see it directly, but we can infer its presence from its effect on visible matter. One of the great challenges of modern astrophysics is that dark matter is both everywhere and nowhere at the same time. It shapes the structure of the universe, yet it is undetectable by any of the traditional methods we use to observe the cosmos. One particularly exciting frontier in the study of dark matter is its potential connection to other unsolved mysteries of the universe, such as dark energy. While dark matter is believed to make up about 27% of the universe's mass energy content, dark energy is thought to account for about 68%. Dark energy is the mysterious force that is causing the accelerated expansion of the universe. Some theorists speculate that dark matter and dark energy might be linked in some way, and understanding one could lead to breakthroughs in understanding the other. But even more fundamental than this connection is the mystery of why dark matter exists at all. What role does it play in the evolution of the universe? If we understand dark matter, will we be able to solve other great cosmic puzzles, such as the formation of galaxies, the behavior of gravity at large scales, and perhaps even the fate of the universe itself? Despite the many unknowns, the search for dark matter continues to push the boundaries of science. Experiments are underway to detect dark matter directly, using extremely sensitive detectors located deep underground, far away from cosmic radiation. Observatories are studying the cosmic microwave background, the afterglow of the Big Bang, for clues about how dark matter influenced the early universe. And theoretical physicists are developing new models to explain how dark matter fits into the framework of particle physics and cosmology. Dark matter is a key piece of the puzzle that is our universe. While we cannot see it, we know it is there, shaping the cosmos in profound ways. Its discovery, once it occurs, could revolutionize our understanding of the universe and everything in it. Until then, dark matter remains a tantalizing mystery, a concept that challenges our understanding of physics and promises to reveal new truths about the nature of reality itself. String theory. String theory might just be one of the most ambitious ideas in modern physics, yet it remains a deeply mysterious and highly debated concept. What makes it so intriguing is that it attempts to solve the grandest question of all. How does everything in the universe, every particle, every force, every interaction, fit together into one unified picture? The human quest to understand the fundamental nature of the universe has been a long one. For centuries, philosophers, scientists, and thinkers have grappled with the question of what the universe is made of and how it works at the most basic level. In the 20th century, we unlocked many of the secrets of the universe through quantum mechanics and general relativity. But these two frameworks have never quite been able to come together. String theory is a bold and radical attempt to do just that, to reconcile the quantum world of the very small with the vast expanses of space-time described by general relativity. Imagine trying to build a perfect, beautiful picture of the universe. You have two jigsaw puzzles. One puzzle contains the quantum world of subatomic particles, where the laws of physics are strange and counterintuitive, and the other puzzle describes the cosmos itself, from the planets and stars to the very fabric of space-time. The trouble is, the pieces from both puzzles don't seem to fit together. One puzzle is based on the tiny, discrete, and probabilistic interactions of particles, while the other is based on the smooth and continuous structure of the universe. String theory proposes that the way to complete the picture is to look at the smallest pieces of all, tiny vibrating strings that form the fundamental building blocks of everything. The journey of string theory begins in the 1960s when physicists were attempting to understand the behavior of subatomic particles. At the time, particle physics was a booming field, as scientists were discovering new particles almost every year. These particles were understood to be point-like objects, meaning that they had no internal structure, they were just small points in space. However, as physicists probed deeper, they began to encounter problems. The equations that describe these point particles didn't seem to make sense when pushed to their extremes. They would break down, predicting infinite energies or unphysical results. This pointed to a deeper issue, a need for a more fundamental description. Enter string theory. The initial idea came from an observation made while studying the strong nuclear force, the force responsible for holding the nucleus of an atom together. The equations for the strong force were complex, but researchers at the time realized that these equations looked very similar to the mathematics describing the vibrations of strings. It was an intriguing observation that would set the course for a new theory in physics. In string theory, the fundamental objects that make up the universe are not point particles, but tiny, vibrating strings. Just as a guitar string can vibrate in different patterns, so too can the strings in string theory vibrate in different ways. These different vibrational patterns correspond to different particles, like electrons or quarks. What string theory proposes is that all the particles and forces we observe in nature are simply different manifestations of the same underlying object, vibrating strings. This is a radical departure from our previous understanding of particles. Instead of thinking of them as individual points, string theory suggests that they are more like tiny, one-dimensional strings, which can stretch and vibrate in various ways. These vibrations determine the properties of the particles, such as their mass, charge, and other characteristics. In this sense, the theory suggests that all the fundamental forces of nature, from gravity to electromagnetism, can be understood as different aspects of the same underlying reality. One of the most mind-boggling aspects of string theory is that it requires more than the 3 spatial dimensions we experience in everyday life. According to string theory, the universe is made up of additional dimensions that are compactified or curled up so small that we can't directly observe them. In the simplest version of string theory, there are 10 dimensions, 9 of space and 1 of time. These extra dimensions are not directly visible to us because they are thought to be curled up at incredibly small scales on the order of the Planck length, which is roughly 10 × 35 meters. To put that in perspective, if the size of a string were the size of a tree, these extra dimensions would be smaller than the tiniest subatomic particles. While we can't see these dimensions, string theory suggests that they exist and that they have a profound impact on the physics of the universe. To visualize this, think of a garden hose. From a distance, it looks like a one-dimensional object, a long cylindrical shape. But if you zoom in and look at the hose closely, you'll notice that it actually has a circular cross-section. In a similar way, string theory posits that extra dimensions are curled up in such a way that we can't detect them in our everyday experience, but they affect the behavior of particles and forces. These extra dimensions provide the framework for string theory to unify all the fundamental forces of nature. In the familiar 3-dimensional space, we experience gravity, electromagnetism, and the strong and weak nuclear forces as separate entities. But in the multidimensional world of string theory, all these forces are thought to be part of a unified whole, different manifestations of the same fundamental phenomenon. Another key ingredient of string theory is supersymmetry. Supersymmetry is a theoretical symmetry between 2 basic types of particles, bosons and fermions. Bosons are particles that carry forces, like photons, which carry the electromagnetic force, or gluons, which carry the strong force. Fermions, on the other hand, are particles that make up matter, like electrons, protons, and neutrons. In supersymmetry, every particle would have a superpartner with a different spin. For example, the photon, which has no mass and a spin of 1, would have a superpartner called the photino, which is a type of fermion. Similarly, the electron would have a superpartner called the selectron, which is a boson. Supersymmetry would thus double the number of particles in the standard model of particle physics. While supersymmetry has yet to be experimentally confirmed, it plays an important role in string theory. The existence of supersymmetric particles helps make the theory more mathematically consistent and provides a natural way to unify the forces of nature. Without supersymmetry, string theory would run into problems, particularly with the way the theory treats quantum mechanics and gravity. One of the main reasons string theory is so appealing to physicists is that it provides a framework for understanding gravity in the context of quantum mechanics. For decades, gravity and quantum mechanics have been at odds with each other. Quantum mechanics, which governs the behavior of particles at the smallest scales, is fundamentally probabilistic and works through wave functions. Gravity, on the other hand, is a deterministic force described by Einstein's theory of general relativity, which treats space-time as a smooth, continuous fabric that is warped by mass and energy. String theory offers a way to reconcile these two theories. In string theory, gravity is mediated by a particle called the graviton, which is a type of boson. The graviton is associated with the vibrations of the string in much the same way that other particles, like photons, arise from different vibrational modes of the string. This makes string theory the only known framework that is capable of describing gravity alongside the other three fundamental forces of nature: electromagnetism, the strong nuclear force, and the weak nuclear force. The idea that gravity is mediated by a quantum particle like the graviton leads to the possibility of quantizing gravity, something that has eluded physicists for decades. If string theory is correct, it could offer a way to describe the quantum aspects of gravity, something that could ultimately lead to a unified theory of everything, a theory of everything, TOE, that explains all the forces and particles of the universe within a single framework. Despite its elegant mathematical structure, string theory remains a speculative theory, as it has yet to produce direct experimental evidence. The problem lies in the fact that the energy scales at which string theory becomes relevant are far beyond the reach of current particle accelerators. The smallest scales at which string theory operates are the Planck scale, which is around 10⁻35 meters. This is orders of magnitude smaller than the scales we can probe with current technology. Scientists are hopeful that advances in particle accelerators, such as the Large Hadron Collider, LHC, might one day provide indirect evidence of string theory. For example, if supersymmetry is correct, we should observe the existence of supersymmetric particles at the LHC. Additionally, string theory makes predictions about the behavior of black holes and the structure of space-time at the quantum level, which could be tested with observations of the cosmos. In the meantime, string theory continues to be a rich field of theoretical research. It has led to profound insights into the nature of space, time, and the fundamental forces of the universe. Whether or not string theory will eventually be confirmed by experiment remains to be seen, but its beauty and elegance make it one of the most compelling ideas in modern physics. String theory is a vision of the universe that unites all the forces and particles of nature into a single, cohesive framework. It proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings are the key to unlocking the mysteries of the cosmos, from the nature of gravity to the unification of the forces of nature. While string theory has yet to be experimentally confirmed, its potential to solve some of the most profound questions in physics makes it a tantalizing area of research. Whether or not it turns out to be the final theory of everything, string theory has already changed the way we think about the universe, opening up new avenues of inquiry and showing us that the true nature of reality might be far stranger and more beautiful than we can even imagine.